Welcome to our exploration of quantum gravity, a captivating field at the intersection of two of the most profound theories in physics, quantum mechanics and general relativity. This topic not only challenges our understanding of the universe, but also pushes the boundaries of modern physics. In this journey, we'll delve into what quantum gravity really means and why it holds such significance in our quest to comprehend the fundamental nature of reality. As we traverse this complex terrain, we'll uncover the major questions that scientists are grappling with today. We'll start with the basics of quantum mechanics, where we will discuss its core principles, including wave-particle duality and the uncertainty principle. These ideas fundamentally change our perception of particles and their behavior at the smallest scales. Next, we'll transition to general relativity, examining how Einstein's groundbreaking theory reshaped our understanding of gravity as the curvature of spacetime. It's crucial to grasp how these two theories operate in their respective realms before we can appreciate the challenges in merging them. One of the main drivers behind the study of quantum gravity is the recognition of the conflicts that arise when we apply quantum mechanics to gravitational phenomena. We will explore these conflicts, particularly at the Planck scale, where the effects of both theories become significant. As we dive deeper, we will discuss the various approaches researchers are taking to resolve these conflicts. String theory and loop quantum gravity are two leading contenders, each with its unique perspectives and methodologies. Throughout our exploration, we will also touch on the holographic principle, a fascinating concept that suggests our universe may be represented as a lower-dimensional information structure. This idea has profound implications for our understanding of black holes and quantum gravity. We won't shy away from discussing experimental approaches as well. While quantum gravity remains a theoretical pursuit, scientists are seeking ways to test these concepts through experiments in particle physics and cosmology. Finally, we will reflect on the future of quantum gravity. What are the unresolved questions that continue to challenge physicists? What breakthroughs might lie ahead? And how could they reshape our understanding of the universe? Join us as we embark on this intellectual adventure into the depths of quantum gravity, where the mysteries of the universe await. Let's begin with the cornerstone of quantum mechanics, the concept of superposition. In this framework, particles can exist in multiple states simultaneously until observed or measured, fundamentally altering our understanding of reality. Next, we encounter wave-particle duality, which posits that particles, such as electrons and photons, exhibit both wave-like and particle-like behavior. This duality challenges our classical intuitions and leads to profound implications for how we perceive the behavior of matter and energy. The Heisenberg uncertainty principle is another pivotal idea in quantum mechanics. It states that the more precisely we know a particle's position, the less precisely we can know its momentum, highlighting the intrinsic limitations of measurement at quantum scales. Quantum entanglement further complicates our understanding of locality and separability. When particles become entangled, the state of one particle is directly linked to the state of another, regardless of the distance between them, leading to intriguing phenomena that defy classical explanations. Moving on, we have quantum tunneling, a process that allows particles to pass through energy barriers that they seemingly shouldn't be able to cross. This phenomenon has applications in various fields, from nuclear fusion to the functioning of semiconductor devices. In quantum mechanics, the concept of quantization plays a crucial role. It describes how certain properties, like energy, are not continuous, but rather exist in discrete levels or states. This quantization leads to the unique behaviors we observe in atomic and subatomic systems. The role of observers in quantum mechanics cannot be understated. The act of measurement not only reveals the state of a system but also influences it, a concept that has led to philosophical debates about the nature of reality itself. Next, we explore the idea of probability amplitudes. In quantum mechanics, instead of deterministic outcomes, we calculate probabilities for different outcomes, fundamentally changing our expectations of how events unfold at the quantum level. Another important principle is the concept of wave function collapse. When a measurement occurs, the wave function, representing all possible states of a quantum system, collapses to a single state, determining the outcome of the measurement. The implications of quantum mechanics extend into the realm of quantum field theory. Here, particles are viewed as excitations in their respective fields, providing a more comprehensive framework for understanding particle interactions. Quantum mechanics also introduces the concept of indistinguishability among particles. In systems of identical particles, their exchange can lead to different statistical behaviors, which are key to understanding phenomena like superconductivity and superfluidity. Lastly, the role of symmetry in quantum mechanics is essential. Symmetries can lead to conservation laws and play a significant role in the formulation of quantum theories, providing deeper insights into the fundamental structure of the universe. Wave-particle duality is a fundamental concept that reveals the dual nature of matter and light. At times, particles behave like waves, spreading out and creating interference patterns, while at other moments they act as discrete entities, showing localized impacts. The famous double-slit experiment illustrates this phenomenon beautifully. When light or electrons are fired through two closely spaced slits, they create an interference pattern, suggesting they are behaving as waves, even when sent one at a time. However, if we attempt to observe which slit a particle passes through, the interference pattern disappears. This alteration in behavior highlights how the act of measurement influences the system, a key tenet of quantum mechanics. This duality isn't limited to photons. It applies to all quantum particles. Electrons, protons, and even larger molecules display both wave-like and particle-like characteristics, leading to profound implications for our understanding of reality. The concept of a wave function encapsulates this duality, describing the probability distribution of a particle's position. Before measurement, the particle exists in a superposition of all possible states, characterized by its wave-like properties. One of the intriguing aspects of wave-particle duality is its challenge to classical physics. In the classical realm, objects are either particles or waves, but quantum mechanics blends these definitions, requiring a new framework for interpretation. De Broglie's hypothesis introduced the idea that all matter has an associated wavelength. This groundbreaking insight laid the groundwork for the development of quantum mechanics, demonstrating that matter is not solely particle-like. In practical terms, wave-particle duality has significant implications for technology. Devices like electron microscopes leverage the wave properties of electrons, allowing us to visualize structures at the atomic level with remarkable precision. Philosophical questions arise from wave-particle duality, particularly regarding the nature of reality. Does a particle have definite properties before measurement, or do these properties only emerge upon observation? This dilemma continues to provoke thought and debate among scientists and philosophers alike. Furthermore, wave-particle duality is essential for understanding phenomena like quantum entanglement. The interconnectedness of particles and their simultaneous influences hinge on the wave-like behavior of quantum states. Exploring wave-particle duality leads to the realization that our intuitive grasp of the universe may be fundamentally flawed. Instead of a clear-cut distinction between waves and particles, we encounter a more nuanced reality that defies everyday experiences. Ultimately, this duality is a window into the bizarre world of quantum mechanics. It challenges our perceptions and invites us to reconsider what we know about the fundamental building blocks of nature. The Heisenberg uncertainty principle stands as a cornerstone of quantum mechanics, fundamentally challenging our understanding of measurement. It states that certain pairs of physical properties, like position and momentum, cannot both be precisely known at the same time. This inherent limitation is not due to experimental imperfections, but arises from the very nature of quantum systems. When we try to measure one property more accurately, the other becomes increasingly uncertain, highlighting a profound truth about the quantum world. To illustrate this, consider a particle. If we attempt to pinpoint its exact position, we can do so, but in doing so, we lose precision in determining its momentum. This interplay reveals a deeper complexity in how particles behave at microscopic scales. The principle is often expressed mathematically, incorporating Planck's constant, which serves as a scale for these uncertainties. This constant underscores the quantized nature of reality, bridging the gap between the macroscopic world we experience and the bizarre quantum realm. Heisenberg's insights revolutionized not just physics, but also philosophical thought about the nature of reality. The idea that reality can be inherently uncertain challenges long-held beliefs about determinism and predictability in the universe. Quantum systems are often described using wave functions, which encapsulate probabilities rather than certainties. The uncertainty principle indicates that these probabilities are not mere limitations of measurement but fundamental characteristics of particles themselves. In practical terms, the implications of this principle extend to various fields, including chemistry and materials science. Understanding electron behavior in atoms, for instance, relies heavily on recognizing the uncertainties involved in their positions and energies. The uncertainty principle also plays a critical role in quantum mechanics applications, such as quantum computing. The inherent uncertainties can be harnessed to process information in ways that classical systems cannot, opening up new avenues for technological advancement. Moreover, the principle has led to discussions about the role of the observer in quantum mechanics. It suggests that the act of observation itself influences the properties of a system, raising questions about the nature of reality and our interaction with it. This uncertainty is not limited to individual particles. It extends to larger systems as well. In fact, the principle has implications for our understanding of chaos theory, where small changes can lead to vastly different outcomes. As we contemplate the uncertainty principle, we recognize it as more than just a mathematical constraint. It invites us to rethink our relationship with the universe, pushing the boundaries of what we consider knowable and challenging our perceptions of reality. Ultimately, the Heisenberg uncertainty principle reveals a universe that is intricate and unpredictable. Embracing this complexity opens new paths for inquiry and understanding in the ever-evolving field of quantum physics. Quantum field theory represents a significant advancement in our understanding of the fundamental forces of nature. It combines classical field theory with quantum mechanics, allowing us to describe particles as excitations in their respective fields. At its core, quantum field theory posits that every particle corresponds to a field that permeates the universe. When these fields are excited, they manifest as particles, which can be observed and measured. The framework allows for the creation and annihilation of particles, a departure from traditional views of particle physics. This flexibility accommodates phenomena like virtual particles, which exist transiently during interactions, influencing observable effects. In quantum electrodynamics, one of the first successful quantum field theories, electromagnetic interactions are described through the exchange of virtual photons. This theory accurately predicts a range of phenomena, including the fine structure of hydrogen and the anomalous magnetic moment of the electron. Quantum chromodynamics extends this idea to the strong nuclear force, governing the interactions of quarks and gluons. By understanding how these fundamental particles interact, we gain insights into the behavior of protons and neutrons within atomic nuclei. The unification of the electromagnetic force and the weak nuclear force in electroweak theory marks another milestone in quantum field theory. This framework paves the way for the standard model of particle physics, which encapsulates our current understanding of the fundamental particles and forces. Symmetry principles play a crucial role in quantum field theory. They dictate how fields and particles behave, leading to conservation laws that govern physical interactions and outcomes. Renormalization is a vital technique employed in quantum field theory to handle infinities that arise in calculations. By systematically removing these infinities, physicists can make meaningful predictions about particle interactions. Quantum field theory also facilitates the study of phase transitions, such as those seen in condensed matter physics. Understanding these transitions requires an appreciation of how fields interact and change under varying conditions. Despite its successes, quantum field theory encounters challenges, especially in merging with gravity. The quest for a quantum theory of gravity remains one of the biggest unsolved problems in physics, pushing researchers to explore new avenues. The implications of quantum field theory extend beyond particle physics. It informs various branches of science, influencing our understanding of phenomena in cosmology, material science, and beyond. As we continue to explore quantum field theory, we find it to be a rich and complex tapestry. This intricate framework not only describes the universe at the smallest scales, but also provides a lens through which we can investigate the very fabric of reality. Quantum entanglement is a phenomenon where particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of the distance separating them. This behavior defies classical intuitions about locality, and suggest that information can be shared across vast distances instantaneously. The concept was famously illustrated in the thought experiment known as Schrödinger's cat. In this scenario, a cat in a sealed box is both alive and dead until observed, highlighting how entangled particles exist in superposition until a measurement is made. Entangled particles exhibit correlations that cannot be explained by classical physics. When one particle's state is measured, the outcome will be correlated with the other particle's state, even if they are light years apart. This raises profound questions about the nature of reality and information transmission. Non-locality is a term that arises from this entanglement, challenging traditional notions of space and time. In classical physics, information cannot travel faster than the speed of light, yet entangled particles seem to communicate instantaneously, leading to debates about the fundamental structure of the universe. This phenomenon was put to the test in a series of experiments, most notably those inspired by Bell's theorem. These experiments confirmed the predictions of quantum mechanics, showing that entangled particles indeed display non-local correlations, further solidifying the reality of quantum entanglement. Entanglement has significant implications for quantum computing and quantum communication. It allows for the creation of qubits that can perform complex calculations simultaneously, vastly increasing computational power compared to classical systems. Quantum cryptography leverages the principles of entanglement to enhance security in communication. Techniques such as quantum key distribution ensure that any attempt to intercept the information alters the entangled state, alerting the parties involved to potential breaches. The philosophical implications of entanglement are vast, challenging our understanding of determinism and the role of the observer. If the act of measurement influences entangled states, it raises questions about the observer's role in shaping reality. Entanglement also plays a crucial role in discussions about the nature of spacetime. Some theories suggest that entanglement could be a fundamental feature of spacetime itself, reshaping our understanding of how particles and fields are interconnected. Researchers are actively investigating potential applications of entanglement in areas such as teleportation and advanced sensors. The ability to transfer quantum states instantaneously could revolutionize how we think about information transfer and communication technologies. As we delve deeper into quantum entanglement, we recognize it as a gateway to understanding the strange and often counterintuitive nature of quantum mechanics. This phenomenon invites us to rethink our assumptions about how the universe operates at its most fundamental level. Ultimately, quantum entanglement not only challenges our classical intuitions, but also opens new pathways for technological innovation and philosophical inquiry. Its profound implications continue to inspire curiosity and exploration in the realms of physics and beyond. Einstein's theory of general relativity revolutionized our understanding of gravity, framing it not as a force, but as the curvature of spacetime. According to this theory, massive objects like planets and stars bend the fabric of spacetime, influencing the motion of other objects around them. The fundamental idea of general relativity is encapsulated in the famous equation, which relates energy, mass, and the geometry of spacetime. This relationship explains how the presence of mass can alter the paths taken by objects in motion, leading to phenomena such as the orbits of planets. One of the key predictions of general relativity is the bending of light around massive objects, known as gravitational lensing. This effect has been observed in numerous astronomical phenomena, providing strong evidence for the validity of Einstein's theory. Black holes are another fascinating outcome of general relativity. These regions of spacetime exhibit gravitational forces so intense that nothing, not even light, can escape their grasp, leading to intriguing questions about the nature of singularities. The concept of time dilation is an essential aspect of general relativity. It posits that time passes more slowly in stronger gravitational fields, which has been confirmed through experiments involving precise atomic clocks at different altitudes. General relativity also provides the foundation for modern cosmology, offering insights into the dynamics of the universe. The expansion of the universe, as described by the Friedmann equations, stems from general relativity and has profound implications for our understanding of cosmic evolution. The theory's predictions extend to phenomena like gravitational waves, ripples in spacetime caused by the acceleration of massive objects. The detection of these waves by observatories such as LIGO has confirmed yet another aspect of Einstein's groundbreaking work. Einstein's theory has withstood rigorous testing over the decades, demonstrating its remarkable accuracy in describing gravitational interactions. It continues to be a critical framework for understanding astrophysical phenomena and the large-scale structure of the universe. Despite its successes, general relativity encounters challenges when combined with quantum mechanics. The quest for a unified theory that reconciles these two pillars of physics remains one of the most profound issues in contemporary science. General relativity also invites philosophical considerations about the nature of space and time. It prompts questions about how we perceive these dimensions and their interconnectedness, reshaping our understanding of reality. As we study general relativity, we appreciate its profound impact not only on physics, but also on our broader understanding of the universe. This theory has forever changed the way we think about gravity, space, and the very fabric of existence. The curvature of space-time is a central concept in Einstein's theory of general relativity, fundamentally altering our understanding of gravity. Rather than viewing gravity as a force acting at a distance, it is seen as a geometric property of space-time itself. Massive objects, such as planets and stars, create distortions in the fabric of space-time around them. These curves dictate how other objects move, causing them to follow paths influenced by the shape of the space-time they traverse. Visualizing this concept can be helpful. Imagine placing a heavy ball on a stretched rubber sheet. The ball causes the sheet to sag, and smaller objects placed nearby will roll towards the heavier mass, much like how planets orbit stars due to the curvature they create. This curvature has profound implications for the passage of time. In regions of stronger gravitational fields, such as near a massive body, time flows more slowly compared to areas of weaker gravity, a phenomenon known as gravitational time dilation. The effects of space-time curvature extend beyond local systems to the cosmos. For instance, light passing near a massive object can bend due to the curvature, leading to observable phenomena such as gravitational lensing, where distant galaxies appear distorted. Understanding the curvature of spacetime also provides insights into black holes. These regions are characterized by extreme curvature, where spacetime becomes so warped that it forms an event horizon, beyond which nothing can escape. Cosmic events, such as the collision of neutron stars, create ripples in spacetime known as gravitational waves. These waves carry information about their origins, allowing us to explore some of the most violent and energetic processes in the universe. The curvature of spacetime can be mathematically described using the Einstein field equations. These equations relate the geometry of spacetime to the distribution of mass and energy, creating a framework for understanding gravitational phenomena. In cosmology, the curvature of spacetime influences the evolution of the universe itself. Models of the universe's expansion, including the effects of dark energy, are deeply rooted in our understanding of how spacetime behaves on a grand scale. This concept also raises philosophical questions about the nature of reality. If space and time are intertwined and affected by mass, what does this mean for our perception of these dimensions? Experiments and observations continue to test the predictions stemming from spacetime curvature. The consistency of these results reinforces the robustness of general relativity as a framework for understanding gravitational interactions. As we explore the curvature of spacetime, we uncover a complex and fascinating picture of how gravity shapes the universe. This intricate relationship between mass, space, and time challenges us to rethink our assumptions about the nature of reality. Gravity as a geometric property fundamentally changes how we conceptualize this force. In general relativity, gravity is not seen as a force transmitted through space, but as the result of the curvature of spacetime itself. This perspective allows us to describe gravitational interactions using geometry rather than traditional forces. Massive objects create dents in the fabric of spacetime, and these distortions dictate how other objects move through that space. For instance, when a planet orbits a star, it is following the curved path defined by the spacetime geometry around the star. The planet's trajectory is a natural outcome of the curvature created by the star's mass. This geometric view explains why objects fall towards one another. Instead of being pulled by a force, they move along the straightest possible paths in curved spacetime, a concept known as geodesics. The implications of gravity as a geometric property extend to our understanding of time as well. The presence of mass not only curves space, but also affects the passage of time, leading to fascinating phenomena such as gravitational time dilation. In practical terms, this geometric interpretation has been confirmed through numerous experiments. Observations of satellite motion and the behavior of light near massive objects align perfectly with the predictions of general relativity. Moreover, this approach provides insights into the behavior of black holes. The extreme curvature near a black hole creates conditions where space-time becomes so warped that it leads to the formation of an event horizon. The geometric nature of gravity also influences the evolution of the universe. As cosmic structures form and evolve, the dynamic interplay of mass and curvature shapes the overall geometry of space-time on a grand scale. Mathematically, the geometric description of gravity is articulated through the language of differential geometry. This advanced mathematical framework allows physicists to describe how curvature relates to mass and energy. As we delve deeper into gravity as a geometric property, we discover its relevance in cosmology. Understanding the curvature of spacetime helps us explain the expansion of the universe and the behavior of galaxies over cosmic time. This perspective challenges classical notions of forces and interactions, inviting us to rethink our assumptions. It underscores the intricate relationship between mass, space, and time, revealing a more interconnected view of the universe. Ultimately, understanding gravity as a geometric property not only enhances our comprehension of physical phenomena, but also deepens our appreciation for the elegance of the universe's structure. This framework continues to inspire new inquiries and discoveries in the field of physics. The Einstein field equations are fundamental to understanding the relationship between matter, energy, and the geometry of space-time. They serve as the mathematical foundation for general relativity, describing how mass and energy influence the curvature of space-time. These equations consist of 10 interrelated partial differential equations. Each equation relates the distribution of energy and momentum in space-time to the curvature, providing a comprehensive framework for understanding gravity. One of the key insights from the field equations is that matter tells space-time how to curve, while curved space-time tells matter how to move. This interplay forms the core of Einstein's vision, encapsulating the dynamic nature of gravity. Solving the Einstein field equations can be complex, often requiring advanced mathematical techniques. Different solutions correspond to various physical scenarios, such as black holes, gravitational waves, and cosmological models of the universe. The Schwarzschild solution is a notable example, describing the gravitational field outside a spherically symmetric mass. This solution predicts the existence of black holes and provides insights into their structure and behavior. Another significant solution is the Friedmann-Lemaitre-Robertson-Walker metric, which models an expanding universe. This framework supports our current understanding of cosmological expansion and provides the basis for modern cosmology. Gravitational waves, ripples in space-time caused by accelerating masses, emerge from the field equations. Their prediction led to the eventual detection of these waves, confirming a critical aspect of general relativity. The Einstein field equations also have implications for the study of singularities. These points in space-time, where curvature becomes infinite, raise important questions about the limits of our current understanding and the nature of the universe. Numerous astrophysical phenomena, from galaxy formation to the behavior of neutron stars, can be analyzed through the lens of the field equations. This versatility demonstrates their central role in modern physics. The equations continue to inspire research into unifying general relativity with quantum mechanics. Scientists seek to explore how these equations can coexist with the principles of quantum theory, aiming for a more comprehensive understanding of the universe. Furthermore, numerical simulations based on the Einstein field equations have transformed our ability to model complex gravitational interactions. These simulations enhance our understanding of events like the merger of black holes and the dynamics of gravitational waves. As we investigate the Einstein field equations, we gain profound insights into the fundamental workings of gravity. Their elegance and depth continue to shape our exploration of the universe and our quest for knowledge. Black holes represent one of the most intriguing consequences of Einstein's theory of general relativity. These regions of space-time exhibit gravitational forces so intense that nothing, not even light, can escape their pull. The formation of black holes typically occurs when massive stars exhaust their nuclear fuel and undergo gravitational collapse. As the core collapses, it compresses into an incredibly dense point known as a singularity, where the laws of physics as we know them break down. Singularities are characterized by infinite density and curvature, leading to profound questions about the nature of spacetime. In these extreme conditions, our current understanding of physics reaches its limits, prompting inquiries into what lies beyond. The event horizon marks the boundary of a black hole, beyond which escape is impossible. Once an object crosses this threshold, it becomes irrevocably trapped, adding to the mystery of black holes and their relationship with the rest of the universe. Hawking radiation, proposed by physicist Stephen Hawking, introduces a fascinating aspect of black holes. This theoretical prediction suggests that black holes can emit radiation due to quantum effects near the event horizon, ultimately leading to their slow evaporation over time. Observationally, black holes can be detected through their interaction with surrounding matter. When material falls into a black hole, it forms an accretion disk, generating intense radiation that can be observed with telescopes. Supermassive black holes, found at the centers of galaxies, are of particular interest to astronomers. These colossal entities can contain millions to billions of solar masses and play a significant role in the formation and evolution of galaxies. The study of black holes raises intriguing questions about information loss. When matter falls into a black hole, does the information contained within it disappear forever, or is it somehow preserved? This paradox continues to challenge physicists. In addition to theoretical implications, black holes also serve as laboratories for testing the limits of general relativity. Observations of their behavior, especially during mergers, provide opportunities to explore gravitational interactions in extreme conditions. The relationship between black holes and spacetime curvature is intricate. As they warp the fabric of spacetime, they create dynamic environments that influence the motion of nearby objects and the structure of the universe. Recent advancements in technology, such as gravitational wave detectors, have revolutionized our ability to study black holes. The detection of gravitational waves from colliding black holes has opened new avenues for understanding their properties and the nature of spacetime. As we explore black holes and singularities, we encounter some of the most profound mysteries of modern physics. These enigmatic objects not only challenge our understanding of gravity, but also invite us to rethink the fundamental principles governing the universe. The conflicts between quantum mechanics and general relativity highlight the challenges in unifying our understanding of the universe. These two theories operate remarkably well in their respective domains, but often yield contradictory predictions when applied together. Quantum mechanics excels in explaining phenomena at microscopic scales, focusing on particles and their interactions. In contrast, general relativity provides a comprehensive framework for understanding gravitational forces and the structure of spacetime on cosmological scales. One major conflict arises from the treatment of gravity itself. While general relativity describes gravity as a curvature of spacetime, quantum mechanics treats forces as mediated by particles, leading to difficulties in reconciling the two perspectives. The concept of singularities presents another challenge. In general relativity, these points represent regions of infinite density, where the laws of physics break down. Yet quantum mechanics suggests that such infinities should be avoided, indicating a breakdown of our current theories. The nature of black holes further illustrates this tension. General relativity predicts that information falling into a black hole is lost, while quantum mechanics insists that information cannot be destroyed. This paradox raises critical questions about the fundamental nature of reality. The phenomenon of quantum entanglement complicates matters as well. Non-local correlations observed in entangled particles appear to contradict the local nature of information transmission, suggested by general relativity, leading to debates about the fabric of spacetime. Efforts to create a theory of quantum gravity aim to bridge the gap between these two frameworks. Various approaches, such as string theory and loop quantum gravity, seek to reconcile the principles of quantum mechanics with the geometric understanding of gravity. Renormalization, a technique used in quantum field theory, faces obstacles when applied to gravitational interactions. Unlike other forces, gravity introduces complexities that challenge our ability to remove infinities and make predictions. Experiments designed to test the predictions of both theories are essential for resolving these conflicts. Observational evidence from cosmic events, like black hole mergers and gravitational waves, offers potential insights into the compatibility of quantum mechanics and general relativity. Philosophical implications also arise from these conflicts, prompting us to question our understanding of reality. If the universe operates on fundamentally different principles at microscopic and macroscopic levels, what does that mean for our conception of space and time? The search for a unified theory continues to inspire researchers across various fields, as physicists explore the intersections of quantum mechanics and general relativity. They are driven by the hope of uncovering a more complete understanding of the universe. Ultimately, these conflicts challenge us to rethink our assumptions about fundamental forces and the nature of reality itself. The journey to reconcile quantum mechanics with general relativity remains one of the most exciting and profound endeavors in modern physics. Inconsistencies at the Planck scale reveal the limitations of our current understanding of physics. This scale, approximately 10^10^35 nm, is where the effects of both quantum mechanics and general relativity become equally significant. At this tiny scale, the classical concepts of space and time begin to blur. Quantum fluctuations can create temporary particles, while space-time itself may behave in unpredictable ways, challenging traditional notions of determinism. The energy levels involved at the Planck scale are extraordinarily high, making experimental verification difficult. Current technologies are far from capable of probing these extremes, leaving many questions unanswered about the fundamental nature of reality. Additionally, the concept of space-time itself may need to be re-evaluated. Instead of being a smooth, continuous fabric, space-time might be discrete, leading to profound implications for how we understand gravity and motion at microscopic levels. Singularities, as predicted by general relativity, present a significant inconsistency at the Planck scale. In these scenarios, densities become infinite, indicating that our existing theories break down and a new framework is necessary to describe such extreme conditions. Quantum mechanics, with its probabilistic nature, contrasts sharply with the deterministic predictions of general relativity. This fundamental clash highlights the difficulties in reconciling the two theories at scales where both are relevant. Loop quantum gravity offers one potential resolution by suggesting that spacetime is quantized. In this framework, the smooth geometry of spacetime emerges from a network of discrete loops, providing a way to avoid singularities. String theory also aims to address these inconsistencies by positing that fundamental particles are actually tiny, vibrating strings. This theory suggests additional dimensions and offers a potential pathway for unifying gravity with quantum mechanics. Researchers are actively exploring various models to better understand the dynamics at the Planck scale. These efforts aim to bridge the gap between quantum theory and general relativity, seeking a cohesive framework for the fundamental forces of nature. Understanding the behavior of gravity at the Planck scale could unlock new insights into the early universe. Conditions shortly after the Big Bang likely resembled those described by theories that apply at this minuscule scale. As we investigate these inconsistencies, we face philosophical questions about the nature of reality itself. What does it mean for space and time to behave differently at such extremes, and how does that reshape our understanding of the universe? Ultimately, the exploration of the Planck scale remains a frontier of modern physics. The quest to resolve these inconsistencies could lead to groundbreaking discoveries about the fundamental nature of matter, energy, and the cosmos itself. The black hole information paradox presents a profound puzzle at the intersection of quantum mechanics and general relativity. It arises from the question of what happens to information when matter falls into a black hole. According to general relativity, once information crosses the event horizon, it seems to be lost forever. This loss contradicts a fundamental principle of quantum mechanics, which asserts that information cannot be destroyed. The implications of this paradox have stirred considerable debate among physicists. If information is indeed lost, it challenges our understanding of quantum states and the predictability of physical systems. Stephen Hawking's work on black holes introduced the concept of Hawking radiation, suggesting that black holes can emit particles and gradually lose mass. This emission raises further questions about whether the information that falls into a black hole is irretrievably lost or can somehow be recovered. Some theorists propose that information might be stored on the event horizon itself, encoded in subtle correlations. This idea suggests that while information appears lost to an outside observer, it may still be preserved in some form. Another approach to resolving the paradox involves the concept of fuzzballs from string theory. These theoretical objects imply that black holes do not have singularities at their centers, instead representing a tangle of strings that retain information. Recent research also explores the holographic principle, which posits that all the information contained within a volume of space can be represented on its boundary. This perspective offers a potential framework for reconciling the apparent loss of information in black holes. The ongoing discussions around the information paradox have significant implications for our understanding of quantum gravity. Solving this paradox could lead to breakthroughs in our quest for a unified theory that encompasses both quantum mechanics and general relativity. Experimental evidence continues to play a role in this debate. Observations of black hole mergers and gravitational waves may provide insights into the nature of black holes and the behavior of information under extreme conditions. As researchers delve deeper into this paradox, they are forced to reevaluate foundational principles of physics. This exploration challenges our assumptions about reality and the nature of information itself. The black hole information paradox exemplifies the complexities and intricacies of modern physics. It highlights the need for a more comprehensive understanding of the universe and the interplay between the fundamental forces that govern it. Ultimately, this paradox serves as a catalyst for new theories and innovative thinking in the realm of theoretical physics. The quest to understand what happens to information in black holes remains a central question driving research in this fascinating field. The problem of singularities is one of the most significant challenges in theoretical physics. These points in spacetime are characterized by infinite density and curvature, where our current understanding of the laws of physics fails. In general relativity, singularities appear in scenarios such as black holes and the Big Bang. When matter is compressed to an infinitely small point, traditional equations break down, leaving physicists without a framework to describe what occurs. Singularities raise fundamental questions about the nature of space and time. If these points represent a breakdown of physical laws, what does this imply for our understanding of the universe at extreme scales? The presence of singularities in black holes suggests that the core of these massive entities holds mysteries yet to be unraveled. Within a black hole, the singularity is hidden from the outside universe by the event horizon, making direct observation impossible. Attempts to resolve the problem of singularities have led to various theoretical approaches. Loop quantum gravity proposes that space-time itself is quantized, potentially avoiding singularities by providing a finite description of dense regions. String theory also offers insights by suggesting that fundamental particles are not point-like, but instead have a one-dimensional nature. This framework could change the characteristics of singularities, leading to a more cohesive understanding of their properties. Another intriguing possibility is that singularities might not exist at all, or that they could be resolved by new physics. Concepts like quantum foam suggest that, at the Planck scale, space-time may be dynamic and fluctuate, preventing the formation of singularities. The implications of singularities extend beyond black holes, influencing cosmological models. The initial conditions of the universe, as described by the Big Bang theory, rely on the concept of singularity, prompting questions about the nature of time and the origins of the universe. The search for a theory of quantum gravity aims to address these singularities. By integrating principles of quantum mechanics with general relativity, researchers hope to construct a framework that can describe these extreme conditions without invoking infinities. Philosophical discussions often accompany the exploration of singularities. If singularities represent a failure of our current theories, what does that imply about the completeness of our understanding of the cosmos? As scientists probe the mysteries surrounding singularities, they are compelled to rethink established concepts. This exploration pushes the boundaries of human knowledge and challenges the very foundations of theoretical physics. Ultimately, the problem of singularities serves as a driving force for new theories and discoveries. The quest to understand these enigmatic features of the universe is a central theme in the ongoing dialogue between quantum mechanics and general relativity. Dark energy and dark matter are two of the most enigmatic components of the universe, playing crucial roles in its structure and evolution. While ordinary matter makes up everything we see, these mysterious forms of energy and matter dominate the cosmos, yet remain largely undetectable. Dark matter accounts for approximately 27% of the universe's total mass-energy content. Although it does not emit, absorb, or reflect light, its presence is inferred through gravitational effects on visible matter, such as galaxies and galaxy clusters. The rotation curves of galaxies provide compelling evidence for dark matter. Observations show that stars at the edges of galaxies rotate at speeds that cannot be explained by the mass visible in the form of stars and gas alone, suggesting the existence of unseen mass. In contrast, dark energy is believed to make up about 68% of the universe. This mysterious force is thought to be responsible for the accelerated expansion of the universe, counteracting the gravitational attraction of matter. The discovery of dark energy emerged from observations of distant supernovae. Researchers found that these supernovae were dimmer than expected, indicating that the universe is expanding at an accelerating rate, prompting the hypothesis of dark energy. Models of the universe must account for both dark matter and dark energy to explain its observed behavior. The lambda cold dark matter model, or LCDM, is the leading cosmological model that incorporates these components, describing the large-scale structure of the universe. Despite extensive research, the true nature of dark matter remains elusive. Various candidates have been proposed, including weakly interacting massive particles, or WIMPs, which would interact only through gravity and the weak nuclear force. On the other hand, dark energy poses its own mysteries, with several theories attempting to explain it. One prominent idea is that it represents a cosmological constant, a fixed energy density filling space homogeneously. Alternative theories, such as quintessence, suggest that dark energy could vary over time and space. These models explore the possibility that dark energy might evolve as the universe expands, impacting its dynamics. Observational efforts continue to refine our understanding of both dark matter and dark energy. Projects like the Dark Energy Survey and the Euclid mission aim to map the distribution of galaxies and study the expansion history of the universe, providing critical data. The interplay between dark matter and dark energy raises profound questions about the fundamental structure of the universe. Their coexistence challenges our understanding of gravity and the forces that govern cosmic evolution. As scientists probe these mysteries, they are not only seeking to uncover the nature of dark matter and dark energy, but also aiming to reshape our understanding of the universe itself. The quest to unravel these enigmas continues to drive research in cosmology and fundamental physics. String theory is a theoretical framework that attempts to unify the fundamental forces of nature within a single, cohesive model. Unlike traditional particle physics, which treats particles as point-like objects, string theory posits that these particles are actually one-dimensional strings vibrating at different frequencies. This vibrational nature of strings gives rise to the various particles we observe in the universe. Each type of particle corresponds to a different vibrational state of the string, creating a rich tapestry of possible interactions and properties. One of the remarkable features of string theory is its ability to incorporate gravity alongside the other fundamental forces. By treating gravitational interactions as manifestations of strings, theorists aim to create a more comprehensive understanding of how gravity operates at quantum scales. String theory also suggests the existence of additional spatial dimensions beyond the familiar three. While we perceive a three-dimensional world, string theory typically requires 10 or 11 dimensions, with the extra dimensions compactified or curled up at scales too small to detect. The mathematical structure of string theory relies on advanced concepts from geometry and topology. These mathematical tools allow researchers to explore the implications of string interactions and how they might correspond to observable phenomena. Various versions of string theory exist, including Type 1, Type 2IA, Type YIB, and heterotic string theories. Each of these models offers unique perspectives on how strings interact and the types of particles they can produce. M-theory is an overarching framework that emerged from string theory, unifying the different string theories into a single theory. It proposes that strings can be viewed as higher dimensional objects called membranes, further enriching the landscape of theoretical physics. String theory has made significant strides in addressing some of the challenges posed by quantum gravity. By providing a framework for understanding the unification of forces, it offers potential solutions to long-standing problems in theoretical physics. Despite its elegant mathematics and promising insights, string theory remains largely untested by experiment. The energies required to probe string-scale physics exceed current technological capabilities, leaving many aspects of the theory speculative. The implications of string theory extend into various domains of physics, including cosmology and particle physics. It suggests new avenues for understanding fundamental interactions and the early universe. As researchers continue to explore string theory, they are not only investigating the nature of particles and forces, but also addressing profound questions about the structure of spacetime itself. This quest could reshape our understanding of reality and the fundamental principles governing the universe. Ultimately, string theory stands as one of the most ambitious attempts to unify the laws of physics. Its exploration challenges physicists to think beyond traditional frameworks and embrace a more interconnected view of the cosmos. String theory aims to bridge the gap between quantum mechanics and general relativity by providing a consistent framework for understanding gravity at the quantum level. This approach suggests that all fundamental forces, including gravity, can be described in terms of vibrating strings rather than point-like particles. One of the key ideas in string theory is that it treats gravity as a manifestation of the interactions of strings. In this context, gravitons, the hypothetical particles responsible for transmitting gravitational force, emerge as specific vibrational states of strings. By incorporating gravity into a quantum framework, string theory seeks to resolve issues that arise when attempting to combine general relativity and quantum mechanics. Traditional methods often lead to inconsistencies or infinities, whereas string theory's mathematical structure offers a more elegant solution. In the context of string theory, spacetime is not merely a passive backdrop but an active participant in the dynamics of the universe. The geometry of spacetime is influenced by the behavior of strings, leading to a deeper understanding of how gravity operates on both small and large scales. The existence of multiple dimensions, as proposed by string theory, is another avenue for unifying forces. By allowing for extra dimensions, string theory provides the flexibility needed to reconcile the different forces and their interactions within a single framework. One promising aspect of string theory is its potential to describe the early universe. The conditions present shortly after the Big Bang could be modeled using string dynamics, offering insights into the fundamental processes that shaped our cosmos. String theory also includes various versions and formulations, each contributing unique perspectives on unification. These approaches allow researchers to explore a wide range of implications, leading to different predictions about the nature of particles and forces. Research in string theory has inspired new mathematical techniques and concepts that have broad applications beyond physics. Tools developed to analyze string interactions can be applied in diverse fields, enriching our overall understanding of complex systems. Despite its theoretical elegance, string theory faces significant challenges in experimental verification. The energies required to test its predictions are currently beyond our technological reach, making it difficult to confirm its validity through direct observation. The quest to unify quantum gravity through string theory also raises philosophical questions about the nature of reality. If the universe operates according to the principles of string dynamics, what does this mean for our understanding of space, time, and existence itself? Collaboration across various disciplines is essential as researchers delve into the intricacies of string theory. By drawing on insights from mathematics, physics, and cosmology, scientists aim to build a cohesive understanding of the universe's fundamental principles. Ultimately, string theory stands as a bold attempt to synthesize the disparate elements of modern physics. Its pursuit of a unified theory of quantum gravity continues to inspire exploration and innovation, pushing the boundaries of what we know about the cosmos. Extra dimensions are a fascinating aspect of string theory that extend beyond our familiar three-dimensional space. String theory typically requires additional spatial dimensions, often bringing the total to 10 or 11, depending on the specific formulation. These extra dimensions are thought to be compactified, meaning they are curled up and hidden at scales so small that they remain undetectable by current experimental methods. This compactification allows the extra dimensions to influence physical properties while remaining imperceptible at macroscopic scales. The geometry of these additional dimensions plays a crucial role in determining the types of particles and forces present in the universe. Different configurations can lead to distinct physical laws, offering a rich landscape of possibilities for how the universe could manifest. Calabi-Yau manifolds are one example of how extra dimensions can be structured. These complex shapes provide a way to compactify dimensions in a manner that preserves the symmetries and properties needed for consistency in string theory. Incorporating extra dimensions can also help address certain theoretical challenges. For instance, they offer a potential solution to the hierarchy problem, which questions why gravity is so much weaker than other fundamental forces. The implications of extra dimensions extend to cosmology as well. Some models suggest that the early universe may have experienced dynamics involving these dimensions, influencing the conditions leading to the formation of galaxies and large-scale structures. Extra dimensions could also provide a framework for unifying gravity with the other fundamental forces. By incorporating them into string theory, researchers can explore how gravity emerges alongside electromagnetism and the strong and weak nuclear forces. The exploration of these dimensions raises intriguing questions about the nature of reality. If extra dimensions exist, what does that imply for our understanding of space and time, and how might it reshape our perception of the universe? Experimental efforts continue to search for evidence of extra dimensions. While direct detection remains elusive, indirect evidence could emerge from high-energy particle collisions or cosmic observations that reveal the influence of these hidden dimensions. The mathematical framework of string theory allows for a variety of extra-dimensional scenarios, each with unique predictions. As researchers investigate these models, they aim to uncover the implications for both fundamental physics and cosmology. Moreover, the existence of extra dimensions challenges traditional views of gravity. If gravity can propagate through additional dimensions, it could help explain why gravitational forces appear weaker compared to other interactions. Ultimately, the concept of extra dimensions in string theory invites us to reconsider the very fabric of the universe. This exploration may lead to new insights into the fundamental structure of reality and the forces that govern it. String theory and loop quantum gravity are two prominent approaches in the quest for a unified theory of quantum gravity. Each offers unique insights and frameworks, yet they fundamentally differ in their methodologies and underlying principles. String theory posits that the fundamental constituents of the universe are one-dimensional strings rather than point particles. These strings vibrate at different frequencies, giving rise to the various particles and forces observed in nature. In contrast, loop quantum gravity focuses on quantizing spacetime itself. This approach treats spacetime as a network of discrete loops, suggesting that space is made up of tiny quantized units rather than being a smooth continuum. The dimensions required in string theory extend beyond the familiar 3, typically involving 10 or 11 dimensions. These extra dimensions allow for the unification of forces, but also introduce complexities that complicate direct experimental verification. Loop quantum gravity, however, primarily operates within the framework of four-dimensional spacetime. By attempting to quantize gravity directly, it avoids the need for additional dimensions, focusing on the geometric properties of spacetime. One of the key challenges for both theories is experimental validation. String theory's predictions often occur at energy scales far beyond current experimental capabilities, while loop quantum gravity faces difficulties in deriving clear, testable predictions from its mathematical structure. String theory offers a broader framework, encompassing various forces and particles under a single umbrella. It aims to unify gravity with electromagnetism and nuclear forces, presenting a comprehensive picture of fundamental interactions. Loop quantum gravity, on the other hand, concentrates specifically on gravity. Its focus is on providing a consistent description of gravitational phenomena, particularly in extreme conditions like black holes and the early universe. Philosophically, the two approaches provoke different questions about the nature of reality. String theory encourages a view of the universe as a dynamic, multi-dimensional entity, while loop quantum gravity emphasizes the discrete nature of spacetime and its implications for continuity. Mathematically, string theory employs advanced concepts from algebraic geometry and topology. Loop quantum gravity relies on techniques from differential geometry, creating distinct frameworks for understanding gravitational interactions. Both theories inspire ongoing research and discussion within the physics community. As scientists explore their implications, they continue to develop new mathematical tools and conceptual insights that could lead to breakthroughs in our understanding of the universe. Ultimately, the interplay between string theory and loop quantum gravity serves as a catalyst for innovation. Each approach contributes to the broader dialogue on quantum gravity, challenging our perceptions and deepening our quest for a unified understanding of the cosmos. String theory faces several criticisms, particularly regarding its lack of direct experimental evidence. Many physicists argue that the predictions of string theory occur at energy scales that are currently inaccessible to experimental testing, leading to skepticism about its validity. Another significant challenge lies in the theory's complexity. The mathematical framework of string theory is intricate and requires advanced concepts, making it difficult for researchers to extract clear, testable predictions that can be experimentally verified. Some critics highlight the vast landscape of string theory solutions, known as the string theory landscape. With potentially thousands of ways to compactify extra dimensions, critics question how one can determine which solution accurately describes our universe. The reliance on additional dimensions also raises philosophical concerns. If the extra dimensions posited by string theory are not observable, some argue that the theory lacks empirical grounding and cannot be considered a complete description of reality. Furthermore, string theory has struggled to make definitive predictions regarding black holes. While it provides insights into their properties, critics contend that it does not adequately address the black hole information paradox or the behavior of singularities. Another critique focuses on the difficulty of achieving unification within string theory. While it aims to unite gravity with the other fundamental forces, the intricate nature of the theory has led to challenges in demonstrating this unification in a clear and straightforward manner. Loop quantum gravity presents itself as a competing theory that directly quantizes spacetime without requiring additional dimensions. This simplicity appeals to some physicists who prefer a more straightforward approach to addressing quantum gravity. Theoretical physicists also express concern about the lack of falsifiability in string theory. If the theory cannot be subjected to experimental verification or refutation, it challenges the scientific method's foundation and raises questions about its status as a physical theory. In addition, string theory's extensive use of abstract mathematics can create barriers for physicists from other fields. This complexity may lead to a divide between researchers, limiting collaboration, and hindering interdisciplinary advancements. Funding and resources also pose challenges for string theory research. The high level of specialization required can make it difficult for younger scientists to enter the field, potentially stifling innovation and the introduction of fresh perspectives. Despite these criticisms, string theory remains a prominent area of research. Proponents argue that its rich mathematical structure and potential to unify fundamental forces offer valuable insights into the nature of the universe. As scientists continue to explore the landscape of string theory, ongoing discussions will shape its development. Addressing these criticisms and challenges is essential for advancing the theory and refining our understanding of fundamental physics. Loop quantum gravity, or LQG, is a theoretical framework that aims to reconcile general relativity with quantum mechanics. This approach fundamentally seeks to quantize spacetime itself, proposing that space is composed of discrete, quantized units, rather than being a continuous entity. At the core of LQG is the idea that the geometry of space can be represented by loops. These loops form a network called a spin network, which encodes information about the gravitational field in a way that allows for a finite description of spacetime. One of the significant achievements of loop quantum gravity is its ability to avoid singularities. By quantizing spacetime, LQG provides a framework where gravitational forces can be analyzed without encountering the infinities often associated with black holes and the Big Bang. The mathematical formulation of LQG relies on concepts from differential geometry and quantum theory. By applying these techniques, researchers derive predictions about the structure of space at the smallest scales. LQG predicts that space is granular, consisting of tiny atoms of space that are fundamentally linked to the quantum properties of gravity. This granular nature challenges the classical notion of a smooth spacetime, offering new insights into the fabric of the universe. One of the striking implications of loop quantum gravity is its potential to unify the description of gravity with the principles of quantum mechanics. This unification addresses key issues that arise when trying to apply quantum mechanics to gravitational phenomena. LQG also has implications for the early universe. By describing the dynamics of spacetime at Planck scales, it provides a framework for understanding what happened during the moments immediately after the Big Bang. A crucial aspect of loop quantum gravity is the role of observers in measuring spacetime geometry. Observational effects arising from the quantization of space could lead to observable consequences in high-energy physics or astrophysical phenomena. Research in LQG has led to several intriguing predictions regarding black holes. The theory suggests that black holes have a quantized structure, potentially leading to a resolution of the information paradox associated with their singularities. Despite its theoretical promise, loop quantum gravity faces challenges in deriving testable predictions. While its mathematical framework is compelling, establishing connections to observable phenomena remains an ongoing effort. Collaboration among physicists continues to drive progress in loop quantum gravity. As researchers refine their models and explore new implications, they contribute to a deeper understanding of the fundamental nature of spacetime. Ultimately, loop quantum gravity stands as a bold approach to tackling some of the most profound questions in modern physics. Its exploration of the quantum nature of spacetime encourages a rethinking of established concepts and opens avenues for future discoveries. Spin networks are a fundamental concept within loop quantum gravity, representing the quantum states of the gravitational field. These networks consist of vertices and edges, where the edges correspond to quantized areas, and the vertices represent the quantized volumes of space. In this framework, each edge is assigned a spin, which quantifies the area it represents. These spins arise from representations of the group that describes rotations in three-dimensional space, providing a mathematical structure to the geometry of spacetime. Spin networks evolve over time into what are known as spin foam models. These models offer a way to visualize the dynamics of spin networks as they change, effectively capturing the history of the quantum geometry of spacetime. The transition from spin networks to spin foams represents a step toward understanding how spacetime behaves at the quantum level. Spin foams can be thought of as two-dimensional surfaces that encode the evolution of quantum states over time. One of the key insights provided by spin foam models is that they offer a framework for calculating amplitudes in quantum gravity. These amplitudes describe the probabilities of different geometric configurations occurring in the universe. Incorporating spin foam models into loop quantum gravity allows researchers to explore the dynamics of spacetime more thoroughly. They help bridge the gap between static quantum states and the evolving nature of spacetime, addressing the issue of how geometry changes over time. Mathematically, spin foams are constructed using sophisticated techniques from algebraic topology. This connection enriches the understanding of both the topology of space and the underlying quantum properties. Researchers have developed various spin foam models, each offering unique predictions about the nature of spacetime. These models can differ in their mathematical structures, leading to different implications for the fundamental aspects of gravity and geometry. Spin networks and spin foams have been used to derive results related to black hole entropy. This connection suggests that the microscopic degrees of freedom encoded in the spin network could account for the thermodynamic properties of black holes. The interplay between spin networks and the broader framework of loop quantum gravity continues to be an area of active research. Exploring these connections can lead to new insights into the quantum nature of gravity and the structure of the universe. As scientists refine these models, they may uncover potential experimental signatures. Observations in high-energy physics or astrophysics could provide evidence for the quantized nature of spacetime, suggested by spin networks and spin foams. Ultimately, the study of spin networks and spin foam models is integral to the ongoing quest for a complete theory of quantum gravity. These concepts challenge conventional views of space and time, inviting deeper exploration into the fabric of reality. Loop quantum gravity and string theory present distinct approaches to unifying gravity with quantum mechanics. While string theory proposes that fundamental particles are one-dimensional strings, loop quantum gravity focuses on the quantization of spacetime itself, treating space as a network of discrete loops. In string theory, additional dimensions beyond the familiar 3 are essential for its framework, often requiring 10 or 11 dimensions to describe interactions fully. In contrast, loop quantum gravity primarily operates within 4 dimensions, emphasizing the geometric properties of spacetime without invoking extra dimensions. The mathematical structures used in each theory differ significantly. String theory relies on advanced concepts from algebraic geometry, while loop quantum gravity employs techniques from differential geometry, showcasing the diversity in their theoretical foundations. Loop quantum gravity seeks to avoid singularities by quantizing spacetime, which offers a way to describe extreme gravitational conditions without encountering infinities. String theory, while providing insights into gravity, still grapples with singularities, particularly in black hole scenarios. One of the key distinctions lies in the treatment of gravity. In string theory, gravity emerges from the dynamics of strings, while in loop quantum gravity, it is fundamental and intrinsic to the structure of spacetime itself. Both theories face challenges in making direct experimental predictions, yet their methods of addressing these issues are different. String theory's predictions often lie at energy scales currently unreachable, while loop quantum gravity focuses on phenomena observable at more accessible scales. The implications for cosmology also vary between the two frameworks. Loop quantum gravity offers a specific perspective on the early universe and how spacetime evolved, whereas string theory explores the interplay of forces and particles in a multidimensional context. Loop quantum gravity emphasizes the discrete nature of spacetime, suggesting that space is composed of tiny, quantized units. String theory, however, treats spacetime as a continuous entity, where the fundamental interactions occur through string vibrations. In terms of unification, string theory aims to integrate all fundamental forces under a single framework. Loop quantum gravity, on the other hand, is primarily concerned with quantizing gravity without necessarily providing a comprehensive unification with other forces. Philosophically, each theory raises different questions about the nature of reality. String theory invites contemplation on multidimensional existence, while loop quantum gravity challenges conventional notions of continuity and the fabric of spacetime. The two approaches foster ongoing dialogue within the physics community, each offering unique insights and challenges. As researchers continue to investigate both frameworks, they contribute to the broader understanding of fundamental physics and the universe. Ultimately, the distinctions between loop quantum gravity and string theory highlight the richness of theoretical exploration in the quest to understand quantum gravity. Each theory represents a different path in the pursuit of uncovering the fundamental nature of reality. Loop quantum gravity has intriguing applications in cosmology, particularly concerning the early universe and the Big Bang. By quantizing spacetime, LQG provides a framework to explore the conditions that existed at the universe's inception. One significant implication of LQG is its ability to address the singularity problem. The theory suggests that instead of encountering an infinitely dense state at the Big Bang, the universe could have emerged from a pre-existing state of loop quantum geometry, preventing singularities. This approach leads to the concept of a big bounce, where the universe undergoes a contraction phase before expanding. Such a model offers an alternative to the traditional Big Bang scenario and introduces a new perspective on cosmic evolution. LQG also provides insights into cosmic inflation, the rapid expansion that occurred shortly after the Big Bang. By analyzing the dynamics of spacetime at quantum scales, researchers can explore how inflationary models might integrate with quantum geometry. The quantization of gravity in LQG allows for the investigation of large-scale structures within the universe. By examining how gravity operates on cosmological scales, scientists can better understand the formation and distribution of galaxies and clusters. Another area of interest is the study of black holes within the context of loop quantum gravity. LQG predicts that black holes have a quantized structure, which could lead to new insights into their thermodynamic properties and the nature of their interiors. The implications of loop quantum gravity extend to dark energy and dark matter as well. By providing a framework to analyze these components, LQG might help explain their roles in cosmic dynamics and the accelerated expansion of the universe. Researchers are also exploring the implications of LQG for gravitational waves. Understanding how these waves interact with the quantized structure of spacetime could reveal new phenomena and enrich our understanding of gravitational dynamics. The ability to model the universe's evolution through the lens of LQG offers opportunities for testing predictions against observational data. This could lead to significant advancements in our understanding of the cosmos and the fundamental forces that govern it. LQG has the potential to inspire new cosmological models that challenge existing paradigms. By investigating the quantum aspects of gravity, scientists can explore novel scenarios for the universe's origin and its fate. As research in loop quantum gravity progresses, its applications in cosmology continue to expand. The interplay between quantum geometry and cosmological phenomena fosters a deeper understanding of the universe's structure and dynamics. Ultimately, loop quantum gravity serves as a vital tool in the ongoing exploration of cosmological questions. Its unique approach to quantizing space-time opens new avenues for understanding the nature of reality and the cosmos. The current status of loop quantum gravity is marked by ongoing research and theoretical advancements. While the framework has shown promise in addressing key issues in quantum gravity, several challenges remain that need to be tackled for broader acceptance and application. One significant hurdle is the mathematical complexity of loop quantum gravity. Developing a comprehensive understanding of its underlying principles often requires advanced techniques that can be difficult to interpret and apply in physical contexts. Another challenge lies in deriving clear, testable predictions from LQG. While the theory offers insights into the quantization of spacetime, translating these concepts into observable phenomena remains an ongoing effort. The lack of experimental evidence also poses a barrier to the acceptance of loop quantum gravity. Many predictions fall outside the reach of current technological capabilities, making it challenging to validate the theory through empirical means. Researchers are actively exploring connections between loop quantum gravity and observable astrophysical phenomena. By identifying potential signatures of quantum gravity effects, scientists hope to find opportunities for testing the theory against real-world observations. The integration of loop quantum gravity with established models in cosmology presents both opportunities and challenges. Harmonizing LQG with the standard model of cosmology requires careful consideration of how quantum effects manifest on cosmic scales. Collaboration across disciplines is crucial for advancing research in LQG. Engaging with experimental physicists, mathematicians, and cosmologists can foster innovative approaches and new ideas that may lead to breakthroughs in understanding. The philosophical implications of loop quantum gravity also invite scrutiny. As researchers delve into the nature of spacetime and gravity, they are challenged to reconsider fundamental concepts related to reality and existence. Despite the obstacles, the community of physicists working on LQG remains dedicated to overcoming these challenges. Their commitment to exploring the implications of loop quantum gravity contributes to a deeper understanding of the universe. Progress in numerical simulations of loop quantum gravity has opened new avenues for investigation. These simulations provide valuable insights into how quantum effects influence gravitational dynamics and spacetime structure. The development of new mathematical tools and frameworks is essential for the continued advancement of LQG. As researchers refine their approaches, they are better equipped to tackle the complexities inherent in quantizing gravity. Ultimately, the journey of loop quantum gravity is one of exploration and discovery. The challenges it faces are not insurmountable, and ongoing efforts may lead to significant advancements in the quest for a unified theory of quantum gravity. The holographic principle is a fascinating concept that suggests our three-dimensional reality may be encoded on a two-dimensional surface. This idea implies that all the information contained within a volume of space can be represented on its boundary, much like a hologram. Originating from insights in black hole physics, the principle emerged from the work of theorists like Gerard 't Hooft and Leonard Susskind. They proposed that the entropy of a black hole, which relates to the information it contains, is proportional to the area of its event horizon rather than its volume. This notion challenges our traditional understanding of space and dimensions. If the universe operates according to the holographic principle, it raises questions about the nature of reality and how we perceive dimensions. The holographic principle also offers potential solutions to the black hole information paradox. By suggesting that information is stored on the event horizon, it implies that the information falling into a black hole is not lost, but rather encoded at its boundary. In string theory, the holographic principle finds a natural framework through the AD-CFT correspondence. This correspondence relates a gravitational theory in a higher dimensional space to a conformal field theory defined on its lower dimensional boundary. The implications of the holographic principle extend beyond black holes and string theory. It provides a new lens through which to view quantum gravity, suggesting that spacetime itself may emerge from more fundamental information. Research into the holographic principle has led to innovative ideas about quantum entanglement. It suggests that entangled particles may have a deeper connection, where their correlations can be understood in terms of information encoded on a boundary. Mathematically, the holographic principle prompts explorations into the nature of spacetime and geometry. It invites physicists to reconsider how information is structured and how it influences the fabric of reality. The principle also finds resonance in the study of condensed matter physics. Concepts analogous to the holographic principle have been applied to explore the behavior of strongly correlated systems, revealing insights into their underlying structure. Experimental tests of the holographic principle remain an area of active research. Physicists are investigating whether signatures of holographic behavior can be observed in high-energy physics or astrophysical phenomena. As researchers continue to explore the implications of the holographic principle, it reshapes our understanding of fundamental physics. The idea challenges conventional notions of space and time, opening new avenues for inquiry. Ultimately, the holographic principle serves as a compelling framework for addressing some of the deepest questions in theoretical physics. Its exploration may lead to profound insights into the nature of the universe and the information that underlies it. The connection between black holes and the holographic principle is a profound aspect of modern theoretical physics. It suggests that the information contained within a black hole can be encoded on its event horizon, fundamentally altering our understanding of how information is stored in the universe. When matter falls into a black hole, traditional views suggest that the information is lost. However, the holographic principle posits that this information is preserved in a two-dimensional format, existing at the boundary rather than disappearing entirely. This idea emerged from studies of black hole entropy, where theorists found that the entropy is proportional to the area of the event horizon. This relationship indicates that the amount of information a black hole can store is not dependent on its volume, but rather its surface area. The implications of this connection extend to the black hole information paradox. By suggesting that information is encoded at the event horizon, it provides a potential resolution to the dilemma of whether information is truly lost in black holes. In string theory, the AD-CFT correspondence offers a concrete realization of the holographic principle. It establishes a duality between a gravitational theory in a higher dimensional space and a conformal field theory on its boundary, providing insights into black hole dynamics. This duality allows researchers to study black holes using tools from quantum field theory. By analyzing the boundary theory, they can gain insights into the behavior of black holes, including their thermodynamics and information content. Furthermore, black holes can be viewed as holographic screens. As objects fall into a black hole, their information is theorized to be projected onto the event horizon, maintaining a record of their characteristics. Exploring this connection also raises questions about the nature of spacetime itself. If black holes are holographic, it suggests that spacetime might not be a fundamental aspect of reality, but rather an emergent property arising from more fundamental information. Recent studies have focused on the role of entanglement in this holographic framework. The connections between entangled particles and the information encoded on a black hole's horizon reveal deep insights into the fundamental structure of reality. The idea that black holes can store information challenges classical notions of causality and locality. It prompts a re-evaluation of how we understand gravity, quantum mechanics, and the interplay between them. Researchers are continuing to investigate the implications of this connection in various fields of theoretical physics. The insights gained may pave the way for a more comprehensive understanding of black holes and their role in the cosmos. As scientists explore the relationship between black holes and the holographic principle, They venture into uncharted territories of knowledge. This exploration not only reshapes our understanding of black holes, but also has the potential to redefine the foundations of physics. The AD-S-CFT correspondence is a powerful theoretical framework that establishes a duality between two seemingly distinct theories. It connects a gravitational theory in anti-de Sitter space with a conformal field theory defined on its boundary. This correspondence was first proposed by Juan Maldacena in 1997 and has since become a cornerstone of modern theoretical physics. The idea suggests that a higher dimensional gravitational theory can be fully described by a lower dimensional quantum field theory, providing a bridge between gravity and quantum mechanics. In this duality, the dynamics of gravitational interactions in the bulk can be translated into the behavior of quantum fields at the boundary. This relationship allows researchers to analyze complex gravitational phenomena using tools from quantum field theory. The anti-de Sitter space itself has a negative curvature, which differs from the positive curvature of our universe. This unique geometry allows for a rich structure that facilitates the exploration of various physical scenarios within the context of the correspondence. One of the significant implications of the AD-CFT correspondence is its ability to shed light on black hole physics. By studying the boundary conformal field theory, researchers can gain insights into the thermodynamics and entropy of black holes in the bulk. Furthermore, the correspondence has provided a framework for exploring quantum gravity. It enables physicists to investigate how gravitational effects emerge from quantum entanglement and the relationships between particles in the boundary theory. AD-CFT has also found applications in condensed matter physics, where it serves as a tool for understanding strongly correlated systems. By mapping these systems onto gravitational theories, researchers can explore their behavior in novel ways. The mathematical tools developed within the framework of AD-CFT have proven invaluable in various areas of physics. They provide techniques for calculating observables and understanding the underlying structure of quantum field theories. Despite its successes, the AD-CFT correspondence has limitations. The correspondence primarily applies to theories in anti-de Sitter space, making it challenging to directly relate to our universe, which appears to have a different geometry. Ongoing research seeks to extend the ideas of AD-CFT to more general settings, potentially allowing for applications to cosmological models and other geometries. This exploration could pave the way for deeper connections between gravity and quantum mechanics. As scientists continue to investigate the implications of the AD-CFT correspondence, new insights are likely to emerge. This framework challenges our understanding of fundamental physics and inspires innovative approaches to long-standing problems. The journey through the AD-CFT correspondence illustrates the power of theoretical exploration. By bridging the gap between gravity and quantum field theory, it opens new avenues for understanding the nature of reality and the fundamental forces that shape our universe. Holography presents a compelling framework for understanding quantum gravity by suggesting that our three-dimensional universe may be an emergent phenomenon. This idea aligns with the notion that the fundamental degrees of freedom of a gravitational system can be encoded on a lower dimensional boundary. In the context of black holes, holography provides insights into the nature of information storage. It implies that the information about the matter that falls into a black hole is preserved on its event horizon, a concept that challenges classical ideas about loss of information in gravitational collapse. The holographic principle offers a way to reconcile the apparent contradictions between quantum mechanics and general relativity. By suggesting that spacetime itself may be emergent from more fundamental information, it invites a re-evaluation of how we understand dimensions and gravity. Holography also influences the study of quantum entanglement. It proposes that entangled particles may be connected through a holographic description, indicating that their correlations are fundamentally linked to the information encoded on a boundary. The AD-CFT correspondence serves as a concrete realization of the holographic principle in theoretical physics. This duality allows physicists to explore how gravitational dynamics in a higher dimensional space relate to a lower dimensional quantum field theory. In the pursuit of a theory of quantum gravity, holography offers valuable insights into the nature of spacetime. It encourages researchers to consider the implications of a universe where geometry arises from fundamental information rather than being an intrinsic feature. This perspective can help address questions about the fabric of space-time and the role of gravity in quantum mechanics. The idea that gravity might emerge from quantum entanglement aligns with holographic concepts, suggesting new pathways for research. Investigating holography in relation to quantum gravity also prompts exploration into the nature of time. If space-time is emergent, it raises questions about how time operates and whether it is a fundamental aspect or an emergent feature of a deeper reality. Numerous theoretical developments arise from the interplay between holography and quantum gravity. These ideas have inspired innovative approaches to understanding black holes, cosmological models, and the structure of the universe. Researchers continue to explore the implications of holography for various physical theories. By bridging the gap between quantum mechanics and gravity, holography serves as a catalyst for new ideas and insights. The connection between holography and quantum gravity challenges conventional views of reality. This ongoing exploration invites scientists to rethink fundamental concepts about space, time, and the nature of the universe itself. Ultimately, the relationship between holography and quantum gravity remains an active area of investigation. The insights gained from this connection have the potential to reshape our understanding of the fundamental laws governing the cosmos. The relationship between holography and quantum gravity has profound implications for our understanding of spacetime. If spacetime is emergent from underlying information, it suggests that the geometry of the universe is not fundamental, but arises from more basic elements. This perspective challenges traditional views of spacetime as a continuous fabric. Instead, it implies that spacetime might be granular or discrete, shaped by the information content encoded within it. Information theory plays a crucial role in this framework, providing insights into how data is stored and transmitted. The holographic principle suggests that the information contained within a volume of space can be fully represented on its boundary, prompting a re-evaluation of how we define and understand information. By linking information and space-time, researchers can explore how physical processes relate to information processing. This connection opens up new avenues for investigating the fundamental nature of reality, where information becomes a key player in shaping the structure of the universe. The implications extend to the study of black holes, where information retention becomes a central issue. If information is stored on the event horizon, it offers a potential resolution to the black hole information paradox, suggesting that no information is truly lost. This approach also raises questions about causality and locality. If information can exist in a holographic form, it challenges our classical understanding of how information interacts and propagates through space-time. The exploration of these concepts influences the development of new theories in quantum gravity. By integrating insights from information theory, researchers can refine their models and potentially uncover deeper connections between gravity and quantum mechanics. Additionally, the implications for quantum entanglement are significant. Understanding how entangled particles relate to holographic descriptions could lead to a more comprehensive grasp of their correlations and the underlying structure of reality. In cosmology, these ideas prompt considerations about the evolution of the universe. If space-time is shaped by information, it may provide insights into the dynamics of cosmic expansion and the formation of large-scale structures. As scientists continue to investigate the interplay between space-time and information theory, they are likely to encounter novel phenomena. These discoveries could lead to breakthroughs in our understanding of the fundamental laws governing the universe. The relationship between information and space-time also invites philosophical inquiries about the nature of reality. It challenges us to reconsider how we define existence, knowledge, and the fundamental principles that underpin the cosmos. Ultimately, the implications for space-time and information theory represent a transformative perspective in modern physics. This exploration encourages a deeper understanding of the universe and our place within it, reshaping our fundamental concepts of reality. Causal dynamical triangulations, or CDT, is an innovative approach to quantum gravity that focuses on constructing a coherent model of spacetime. This method employs a combinatorial technique using simple building blocks to create a triangulated version of spacetime that respects causality. In CDT, spacetime is represented as a series of interconnected simplices, which are the higher dimensional analogues of triangles. By varying the number of simplices and their arrangements, researchers can explore different configurations of spacetime. One of the key features of the CDT approach is its emphasis on causality. The triangulations are arranged in such a way that they maintain a consistent causal structure, ensuring that time always progresses in one direction, and that past events cannot influence future ones. This focus on causality distinguishes CDT from other approaches, allowing for a more intuitive understanding of the dynamics of spacetime. By preserving causal relationships, CDT aims to model the emergence of classical spacetime from fundamentally quantum principles. The CDT framework provides a way to compute the path integral of quantum gravity by summing over all possible triangulations. This approach allows physicists to derive meaningful physical predictions from the geometry of spacetime. Researchers have successfully applied the CDT method to various scenarios, including the study of quantum cosmology. By examining the evolution of a universe from a quantum state, CDT helps explore questions related to the early moments of cosmic history. In addition, CDT offers insights into the nature of singularities. By modeling spacetime dynamics at the quantum level, the approach provides a framework to analyze how singularities might be avoided or resolved. Numerical simulations play a vital role in the CDT approach. These simulations help researchers visualize the behavior of triangulated spacetime, offering insights into its structure and the emergence of geometric properties. One of the advantages of the CDT framework is its compatibility with established principles of physics. By incorporating causality and utilizing a discrete representation of spacetime, CDT aligns with our understanding of both general relativity and quantum mechanics. As scientists continue to explore the implications of CDT, they are uncovering new insights into the nature of spacetime. This approach provides a unique perspective on quantum gravity, bridging the gap between the classical and quantum worlds. Ongoing research in CDT aims to refine the models and explore their implications for observable phenomena. By connecting theoretical insights with potential experimental tests, researchers hope to validate the framework and its predictions. Ultimately, the CDT approach contributes to the broader dialogue in quantum gravity research. Its innovative methods and focus on causality offer valuable tools for understanding the fundamental nature of spacetime and the forces that govern it. Spacetime discretization is a fundamental concept in various approaches to quantum gravity, including causal dynamical triangulations. It involves representing spacetime not as a continuous entity but as a network of discrete units or building blocks. In this framework, spacetime is broken down into a finite number of simplices, which can be visualized as higher dimensional triangles. These simplices connect to form a larger structure that approximates the geometry of spacetime while maintaining causal relationships. The idea behind discretization is that at very small scales, such as the Planck scale, spacetime may not be smooth. Instead, it could exhibit a granular structure where distances and intervals are quantized rather than infinitely divisible. This approach allows researchers to apply mathematical techniques from combinatorial geometry and topology. By summing over all possible configurations of discrete spacetime, scientists can explore the implications of quantum effects on the structure of the universe. Discretization also helps address challenges related to singularities in general relativity. By modeling spacetime as a discrete entity, the approach offers a way to avoid infinities that arise in classical theories, providing a more manageable framework for understanding extreme conditions. In the context of causal dynamical triangulations, spacetime discretization preserves causal relationships. This ensures that time flows in one direction and that causality is respected throughout the triangulated structure. Researchers can use numerical simulations to study the behavior of discretized spacetime, allowing them to visualize how quantum effects influence geometric properties. These simulations provide insights into the dynamics of spacetime and how it evolves over time. Spacetime discretization opens up new avenues for investigating quantum gravity. By rethinking the nature of spacetime, physicists can explore the fundamental interactions between geometry and quantum mechanics. The implications of this concept extend beyond theoretical physics. It also influences our understanding of fundamental particles and their interactions, suggesting that these too may be affected by the discrete nature of spacetime. As the study of spacetime discretization continues, Researchers are discovering its potential applications in cosmology and other fields. It offers a fresh perspective on the early universe and how spacetime itself might have originated. The challenge remains to connect these theoretical insights with observable phenomena. By identifying signatures of discretization in experiments or astrophysical observations, scientists can validate these models and their predictions. Ultimately, spacetime discretization serves as a vital concept in the ongoing quest to understand the nature of reality. It invites a re-evaluation of established principles and encourages exploration into the intricate relationship between quantum mechanics and gravity. Causal dynamical triangulations, CDT, offers a unique approach to addressing the complexities of quantum gravity. By discretizing spacetime into a network of simplices, CDT provides a framework for understanding the quantum properties of gravity in a manageable way. This method preserves the causal structure of spacetime, ensuring that time flows in a consistent direction. This respect for causality allows for the exploration of gravitational dynamics while maintaining coherence with established physical principles. In CDT, researchers sum over all possible triangulated configurations of spacetime to compute the path integral. This process enables them to derive meaningful physical predictions regarding the behavior of gravity at quantum scales. One of the primary goals of CDT is to avoid singularities, which often arise in classical general relativity. By modeling spacetime discretely, the framework seeks to circumvent the infinities associated with black holes and the Big Bang. The approach also emphasizes the emergence of classical spacetime from fundamentally quantum processes. As the number of simplices increases, CDT aims to show that the discrete structure can approximate a smooth spacetime, bridging the gap between quantum gravity and classical general relativity. CDT provides insights into the early universe by examining how quantum fluctuations might influence cosmic evolution. This allows researchers to explore scenarios related to the birth of the universe and the dynamics that shaped its initial conditions. The numerical simulations employed in CDT are essential for understanding how spacetime behaves at small scales. By analyzing these simulations, scientists can visualize the interplay between geometry and quantum effects, leading to new insights into gravitational dynamics. Researchers also investigate the relationship between triangulations and physical observables, such as curvature and topology. This analysis helps establish connections between the mathematical structure of spacetime and the properties of physical systems. CDT's focus on causality and the discrete nature of spacetime challenges traditional views of gravity. It encourages a re-evaluation of how we understand gravitational interactions and the fundamental principles governing them. The framework's compatibility with established theories is another strength of CDT. By aligning with the principles of general relativity, it offers a coherent path forward in the quest for a unified theory of quantum gravity. As research in CDT progresses, the aim is to refine the models and explore their implications for observable phenomena. This connection to experimental validation is crucial for assessing the framework's relevance and accuracy in describing the universe. Ultimately, CDT's approach to solving quantum gravity represents a promising direction in theoretical physics. By focusing on the discrete and causal nature of spacetime, it opens up new avenues for understanding the fundamental forces of nature. Causal dynamical triangulations, CDT, distinguishes itself from other approaches to quantum gravity, such as loop quantum gravity, LQG, and string theory. While LQG focuses on the quantization of spacetime itself, CDT emphasizes a discrete structure that preserves causality throughout its triangulated representation. In LQG, spacetime is modeled as a network of loops, where geometry emerges from the quantum properties of these loops. CDT, on the other hand, utilizes simplices to build a causal framework, allowing for a different interpretation of how spacetime behaves at the quantum level. String theory proposes that fundamental particles are one-dimensional strings vibrating in higher dimensional spaces. In contrast, CDT works primarily within a four-dimensional context, focusing on the dynamics of a discretized spacetime without requiring additional dimensions. The treatment of gravity varies between these theories. In CDT, gravity is understood through the path integral of discretized triangulations, whereas LQG directly quantizes the gravitational field, leading to different methodologies for analyzing gravitational phenomena. String theory aims for a unification of all fundamental forces, presenting a comprehensive framework that includes gravity. CDT does not necessarily seek to unify forces, but rather to understand the quantum aspects of gravity on its own terms. Numerical simulations play a critical role in CDT, allowing researchers to visualize the behavior of triangulated spacetime. In LQG, the focus is more on mathematical formulations, which can sometimes make direct interpretations more challenging. The approach taken by CDT to avoid singularities contrasts with the methods in string theory and LQG. While LQG seeks to prevent singularities through quantization, CDT aims to model spacetime discretely to circumvent the infinities associated with classical theories. When it comes to cosmological implications, CDT provides insights into the early universe through its discrete structure. String theory also addresses cosmological questions, but its focus is often broader, examining how various forces might emerge from a unified framework. The compatibility of CDT with established principles of physics enhances its appeal among researchers. Both LQG and string theory also strive for consistency with known physics, but their different approaches can lead to distinct conclusions about gravity and spacetime. While all three theories explore quantum gravity, their methodologies and focuses vary significantly. This diversity allows for a rich dialogue among physicists, encouraging the exploration of different avenues in understanding the fundamental nature of the universe. The distinct approaches taken by CDT, LQG, and string theory illustrate the complexity of the quest for quantum gravity. Each framework offers unique insights and challenges, contributing to the ongoing exploration of the universe's underlying principles. Ultimately, the interplay between these different theories enriches the field of theoretical physics. By investigating their differences and similarities, researchers can refine their understanding of gravity, spacetime, and the fundamental forces of nature. The current status of research in causal dynamical triangulations, CDT, is marked by significant advancements and ongoing exploration. Researchers continue to refine the mathematical framework, enhancing the understanding of how discretized spacetime can provide insights into quantum gravity. Numerical simulations have become a critical tool in CDT studies. These simulations allow scientists to visualize the behavior of triangulated spacetime, offering a way to analyze its dynamics and derive meaningful predictions about gravitational phenomena. Recent efforts have focused on improving the algorithms used in these simulations. By optimizing computational techniques, researchers can explore larger and more complex configurations of spacetime, pushing the boundaries of what can be modeled. CDT has also been applied to cosmological models, investigating the early universe's dynamics. This area of research aims to understand how quantum effects might influence cosmic evolution, providing a fresh perspective on the birth of the universe. The implications of CDT for black hole physics are another active area of research. By examining how spacetime behaves near black holes, scientists hope to uncover new insights into their thermodynamic properties and the nature of singularities. Collaboration among researchers is crucial in advancing CDT. Interdisciplinary efforts that draw on expertise from different areas of physics can foster innovative ideas and lead to new avenues for investigation. As the field evolves, researchers are increasingly focusing on connecting CDT to observable phenomena. Identifying experimental signatures of discretization in astrophysical observations could provide vital validation for the framework. Ongoing studies aim to explore the relationship between CDT and other approaches to quantum gravity. By examining how CDT complements or contrasts with theories like loop quantum gravity and string theory, scientists can gain a more comprehensive understanding of the field. The philosophical implications of CDT are also a subject of discussion among researchers. Exploring how discretized spacetime influences our understanding of reality invites deeper inquiries into the nature of existence and the structure of the universe. Funding and resources remain essential for sustaining research in CDT. Adequate support enables scientists to pursue innovative projects and maintain momentum in developing this promising framework. Conferences and workshops focused on quantum gravity increasingly feature CDT as a key topic of discussion. These gatherings facilitate knowledge exchange and collaboration, helping to shape the future directions of research. Ultimately, the current status of CDT research reflects a vibrant and active area of theoretical physics. The ongoing exploration of discretized spacetime continues to inspire new ideas and insights into the fundamental nature of gravity. Black hole thermodynamics is a fascinating field that explores the relationship between black holes and the laws of thermodynamics. It establishes connections between the physical properties of black holes and fundamental concepts such as temperature, entropy, and energy. One of the key insights is that black holes have a temperature known as the Hawking temperature. This temperature arises from the quantum effects near the event horizon, leading to the prediction that black holes can emit radiation. The phenomenon of Hawking radiation was first proposed by Stephen Hawking in 1974. It suggests that particle-antiparticle pairs can form near the event horizon, with one particle falling into the black hole while the other escapes, resulting in a net loss of mass for the black hole. Black hole entropy, another crucial concept, is proportional to the area of the event horizon. This relationship is expressed by the Bekenstein-Hawking formula, which indicates that the entropy of a black hole can be understood in terms of its surface area rather than its volume. This connection between entropy and area leads to profound implications for the nature of information. It raises questions about how information is stored in black holes and whether it can be recovered after the black hole evaporates. The study of black hole thermodynamics has significant implications for the black hole information paradox. If information is lost when matter falls into a black hole, it challenges our understanding of quantum mechanics, which states that information cannot be destroyed. Researchers have also explored the implications of black hole thermodynamics for the early universe. Understanding how these principles apply to primordial black holes can provide insights into cosmic evolution and the formation of large-scale structures. The laws of black hole thermodynamics mirror the laws of classical thermodynamics. For example, the first law of thermodynamics relates changes in energy to changes in mass and entropy, while the second law suggests that the total entropy of the universe increases. These analogies have led physicists to consider whether the universe itself might behave like a thermodynamic system. Exploring the connections between black holes and thermodynamic principles could yield new insights into the fundamental nature of reality. Current research continues to investigate the nuances of black hole thermodynamics. This includes studying the effects of rotation and charge on black hole properties, which can further enhance our understanding of their thermodynamic behavior. As scientists delve deeper into black hole thermodynamics, they are also exploring potential experimental signatures. Observations related to black holes and their emissions could provide valuable data to validate the principles derived from thermodynamic analogies. The exploration of black hole thermodynamics represents an exciting intersection of quantum mechanics, gravity, and thermodynamics. It challenges our perceptions and invites a rethinking of fundamental concepts in theoretical physics. Hawking radiation is a groundbreaking concept that bridges the realms of quantum mechanics and black hole physics. Proposed by Stephen Hawking in 1974, it suggests that black holes can emit radiation due to quantum effects occurring near their event horizons. This process arises from the behavior of virtual particle pairs that constantly form and annihilate in empty space. Near the event horizon, one particle of the pair may fall into the black hole, while the other escapes, resulting in the black hole losing energy and mass. The escaping particle is observed as radiation emitted by the black hole, leading to the idea that black holes are not entirely black. Instead, they can gradually evaporate over time as they emit this radiation. Hawking radiation has profound implications for the understanding of black holes. It challenges the notion that black holes are permanent fixtures in the universe, suggesting that they can eventually disappear as they lose mass. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes emit radiation at higher temperatures, making them more likely to evaporate quickly compared to larger black holes, which radiate at much lower temperatures. This phenomenon raises significant questions regarding the fate of information that falls into a black hole. If a black hole evaporates completely through Hawking radiation, does the information contained within it vanish, or can it be recovered in some way? The black hole information paradox emerges from these questions, creating tension between the principles of quantum mechanics and general relativity. The idea that information could be lost conflicts with the foundational principle that information cannot be destroyed. Current research seeks to resolve this paradox, exploring potential mechanisms for information preservation during black hole evaporation. Concepts like holography and entanglement are being investigated as possible solutions to this fundamental dilemma. In addition to theoretical implications, Hawking radiation presents challenges for experimental verification. Detecting this radiation from astrophysical black holes is extremely difficult due to its weak nature compared to other cosmic phenomena. Some scientists are exploring the idea of creating analogues of black holes in laboratory settings, such as using certain materials to simulate the conditions for Hawking radiation. This could offer insights into the underlying physics and potentially provide experimental validation for the concept. Hawking radiation has also influenced discussions around quantum gravity, providing a framework for examining how quantum effects manifest in strong gravitational fields. By bridging these two domains, it highlights the need for a unified understanding of fundamental forces. Ultimately, the study of Hawking radiation and its quantum effects continues to inspire new research and inquiry. The intersection of quantum mechanics and black hole physics remains a rich area for exploration, challenging our perceptions of the universe. Black hole entropy is a concept that quantifies the amount of information that can be stored within a black hole. Introduced by Jacob Bekenstein and later expanded by Stephen Hawking, it relates to the area of the event horizon rather than the volume of the black hole itself. The Bekenstein-Hawking formula expresses this entropy as proportional to the area of the event horizon divided by the Planck length squared. This relationship implies that black holes have a vast capacity for information storage, challenging traditional notions of entropy and thermodynamics. The idea of entropy in black holes leads to significant implications for the nature of information in the universe. If a black hole can contain information, it raises questions about what happens to that information when matter falls into it. The information loss problem arises from the observation that, according to general relativity, information appears to be lost when an object crosses the event horizon. This challenges the foundational principles of quantum mechanics, which assert that information cannot be destroyed. The evaporation of black holes via Hawking radiation further complicates this issue. As black holes emit radiation and lose mass over time, the question arises, is the information about the matter that fell into the black hole lost forever, or can it be recovered? This paradox creates a tension between the principles of quantum mechanics and the predictions of general relativity. It has led to intense debates among physicists about the fundamental nature of reality and the laws governing the universe. Some researchers propose that information is not lost but rather encoded in the Hawking radiation itself. This would mean that the emitted radiation carries information about the black hole's past, potentially allowing for its recovery. Another perspective involves the holographic principle, suggesting that the information about matter falling into a black hole is stored on the event horizon. This idea implies that the three-dimensional experience of falling into a black hole could be fundamentally linked to two-dimensional data on its surface. Efforts to resolve the information loss problem often explore concepts like quantum entanglement and spacetime topology. By examining how these elements interact, scientists hope to uncover mechanisms that might allow for information preservation. Current research continues to investigate the connections between black hole entropy and quantum gravity. These explorations aim to develop a more comprehensive understanding of how information behaves in extreme gravitational conditions. The implications of black hole entropy and the information loss problem extend beyond theoretical physics. They challenge our perceptions of reality, urging us to rethink foundational concepts such as existence, information, and the nature of the universe. As physicists delve deeper into these issues, new insights are likely to emerge. The exploration of black hole entropy and its connection to the information loss problem remains a vital area of inquiry in the quest for a unified theory of quantum gravity. Quantum gravity near black hole singularities presents one of the most profound challenges in theoretical physics. In classical general relativity, singularities are regions where gravitational forces become infinite, and the laws of physics as we know them break down. At these points, the curvature of spacetime reaches extreme levels, leading to conditions that defy our current understanding. Quantum effects are expected to play a significant role in these environments, but their precise nature remains elusive. One of the key questions is how quantum mechanics interacts with the strong gravitational fields present near a singularity. Traditional models struggle to describe the behavior of matter and energy under such extreme conditions, necessitating a new framework. In approaches like loop quantum gravity, researchers propose that singularities may be avoided altogether. By quantizing spacetime, these theories suggest that the fabric of space itself can prevent infinite density from occurring. Another perspective comes from string theory, which posits that singularities could be resolved by considering higher dimensional effects. The presence of additional dimensions may provide mechanisms for smoothing out the extreme conditions typically associated with singularities. Investigating the quantum behavior of matter near singularities also raises questions about information retention. If quantum gravity can mitigate the effects of singularities, it could lead to a better understanding of how information is preserved in extreme gravitational environments. Current research often employs numerical simulations to explore these scenarios. By modeling the dynamics of spacetime near a black hole, scientists can visualize how quantum effects might alter the classical predictions of general relativity. The relationship between quantum entanglement and black hole singularities is another area of interest. Understanding how entangled particles behave in these extreme conditions could provide insights into the fundamental nature of spacetime. As scientists probe deeper into the nature of singularities, they are forced to re-evaluate foundational concepts about reality. The implications of quantum gravity near singularities could fundamentally change our understanding of black holes and the universe as a whole. Collaborative efforts across various fields of physics continue to drive progress in this area. By integrating insights from quantum mechanics, general relativity, and cosmology, researchers aim to develop a cohesive understanding of the phenomena occurring near singularities. Ongoing investigations also seek to connect theoretical predictions with observational data. Identifying signatures of quantum gravity effects in astrophysical phenomena could validate theories related to black hole singularities. The exploration of quantum gravity near singularities remains an active and dynamic field of research. As physicists strive to understand these enigmatic regions, they contribute to a deeper grasp of the fundamental laws that govern the universe. Observational evidence plays a crucial role in shaping theoretical models in quantum gravity and black hole physics. While direct observations of quantum gravity effects remain elusive, scientists have gathered significant data from astronomical phenomena that hint at the underlying principles. One of the primary sources of observational data comes from gravitational waves detected by facilities like LIGO. These waves, generated by the merging of black holes, provide insights into the properties and dynamics of these massive objects, offering clues about their behavior under extreme conditions. The study of black hole accretion disks also yields valuable information. By observing the radiation emitted from matter falling into a black hole, researchers can infer details about the black hole's mass, spin, and the gravitational effects at play near the event horizon. Additionally, observations of cosmic microwave background radiation give insights into the early universe and its evolution. The patterns and fluctuations in this radiation can provide clues about the conditions present shortly after the Big Bang, which are critical for understanding quantum gravity. Theoretical models continue to evolve based on these observations, integrating new data to refine predictions. For instance, advancements in numerical simulations allow researchers to test the outcomes of various models against observed phenomena, enhancing the accuracy of theoretical frameworks. Hawking radiation, although challenging to detect, remains a focus of theoretical exploration. Efforts to find indirect signatures of this radiation are ongoing, with the hope that future observations could validate predictions related to black hole thermodynamics. The holographic principle also intersects with observational efforts. By exploring whether evidence of holographic behavior can be found in cosmic structures, researchers aim to connect theoretical insights with empirical data. Moreover, theoretical models like causal dynamical triangulations are being tested against existing observations. As researchers investigate the implications of these models, they seek to identify potential discrepancies or confirmations in astronomical data. In cosmology, understanding dark matter and dark energy also informs theories of quantum gravity. Observational evidence from galaxy distributions and cosmic expansion provides a backdrop against which quantum gravity models can be assessed. As scientists continue to refine their theoretical models, they remain vigilant for new observational techniques and technologies. Future telescopes and detectors are expected to enhance our ability to probe the universe, potentially uncovering phenomena that illuminate the nature of quantum gravity. Collaborations between theorists and experimentalists are crucial for advancing our understanding. By sharing insights and findings, they work together to bridge the gap between theoretical predictions and observational realities. Ultimately, the interplay between observational evidence and theoretical models drives the progress of research in quantum gravity and black hole physics. Each new discovery has the potential to reshape our understanding of the fundamental laws governing the universe. Detecting quantum gravitational effects is one of the foremost challenges in contemporary physics. As researchers seek to uncover the fundamental nature of gravity, they are exploring innovative experimental approaches to identify these elusive phenomena. One promising avenue is the study of gravitational waves, which carry information about extreme cosmic events. By analyzing these waves, scientists can investigate how quantum effects might influence gravitational interactions during black hole mergers or neutron star collisions. Another method involves looking for signs of Hawking radiation. While direct detection of this radiation is difficult due to its weak signal, researchers are exploring indirect ways to infer its presence through the study of black hole dynamics and emissions. High-energy particle collisions in facilities like the Large Hadron Collider offer opportunities to probe quantum gravitational effects. By reaching energy scales close to the Planck level, physicists hope to observe phenomena that might hint at the underlying principles of quantum gravity. Experiments designed to test the limits of general relativity in strong gravitational fields are also crucial. Observations of light bending around massive objects can provide insights into how quantum effects might alter the predictions of classical physics. Additionally, researchers are investigating analog black holes created in laboratory settings. By simulating conditions similar to those near actual black holes, scientists can study the behavior of quantum fields and explore the potential emergence of Hawking-like radiation. Quantum entanglement experiments may reveal insights into the interplay between gravity and quantum mechanics. By examining how entangled particles behave in varying gravitational fields, researchers aim to identify any deviations from expected results that could point to quantum gravitational effects. Astrophysical observations, particularly those related to cosmic microwave background radiation, can also yield valuable information. Fluctuations in this radiation may provide clues about the early universe, where quantum gravity played a critical role. Theoretical models, such as those stemming from loop quantum gravity or string theory, inform experimental designs. These models guide researchers in identifying specific signatures or behaviors to look for in their experiments. Interdisciplinary collaboration remains vital for advancing the detection of quantum gravitational effects. By bringing together experts from various fields, scientists can develop innovative techniques and technologies to explore this complex domain. As advancements in technology continue, the ability to detect quantum gravitational effects may become more feasible. New observational tools and experimental setups will enhance the capacity to test the boundaries of current theories and explore the fabric of spacetime. Ultimately, the pursuit of detecting quantum gravitational effects drives progress in our understanding of the universe. Each new finding has the potential to reshape our perspective on the fundamental laws governing gravity and quantum mechanics. Particle colliders play a pivotal role in exploring the fundamental nature of matter and the forces that govern the universe. By accelerating particles to near-light speeds and colliding them, scientists can recreate conditions similar to those that existed shortly after the Big Bang. These high-energy collisions provide insights into the interactions between particles, allowing researchers to probe the fundamental building blocks of matter. By studying the resulting debris from these collisions, physicists can infer the properties of previously undiscovered particles. One of the main objectives of particle colliders is to test predictions from theoretical models, including those related to quantum gravity. The energy scales reached in colliders may offer glimpses into phenomena that could reveal the effects of quantum gravity on particle interactions. For instance, experiments at the Large Hadron Collider have been instrumental in discovering the Higgs boson. This particle is crucial for understanding the mechanism that gives mass to other particles, and its discovery has confirmed several aspects of the standard model of particle physics. In addition to searching for new particles, colliders are used to study the behavior of known particles under extreme conditions. Observations of particle interactions at high energies can provide clues about how these particles behave when influenced by strong gravitational fields. Researchers are particularly interested in potential signs of supersymmetry, a theoretical framework that extends the standard model. If discovered, supersymmetry could provide insights into dark matter and unify the forces of nature. Colliders also facilitate studies on the unification of forces. By examining how different forces interact at high energies, scientists hope to uncover deeper connections between electromagnetic, weak, and strong nuclear forces. The role of particle colliders extends to investigating the properties of quark-gluon plasma, a state of matter that existed in the early universe. Understanding this phase can shed light on the conditions that prevailed shortly after the Big Bang. Moreover, collider experiments can offer insights into the nature of black holes and quantum gravity. High-energy collisions may produce miniature black holes, allowing researchers to study their characteristics and test theories related to quantum gravity. Particle colliders also promote international collaboration, bringing together scientists from around the world to work on groundbreaking research. This cooperative effort fosters the exchange of ideas and expertise, enriching the scientific community. As technology advances, new collider projects are being proposed, aiming to reach even higher energy levels. These future colliders will push the boundaries of current research and expand our understanding of fundamental physics. Ultimately, the role of particle colliders in advancing our knowledge of the universe is invaluable. They serve as essential tools for exploring the fundamental laws that govern matter, energy, and the interactions that shape our reality. Cosmological observations are vital for understanding the universe's history and structure. Among the most significant of these observations is the cosmic microwave background radiation, which provides a snapshot of the early universe just after the Big Bang. The cosmic microwave background, or CMB, is the remnant radiation from the hot, dense state of the universe. It fills the cosmos and offers crucial insights into the conditions that prevailed during the first moments of cosmic expansion. By studying the CMB, scientists can learn about the universe's composition, including the proportions of dark matter, dark energy, and ordinary matter. Detailed measurements of the CMB's temperature fluctuations reveal information about the early distribution of matter and energy. The CMB is remarkably uniform, but slight variations in temperature provide clues about the density fluctuations that led to the formation of galaxies and large-scale structures. These anisotropies are crucial for modeling the evolution of the universe. Observations of the CMB have been enhanced by missions such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite. These missions have provided highly precise measurements, improving our understanding of cosmological parameters and the universe's overall geometry. Additionally, the study of the CMB has implications for quantum gravity. Insights into the fluctuations present at the CMB's formation can inform models of how quantum effects may have influenced the early universe. Cosmological observations extend beyond the CMB, including the study of distant galaxies and supernovae. By measuring the light emitted from these objects, researchers can gain insights into the expansion rate of the universe and the influence of dark energy. Gravitational lensing is another important observational tool. This phenomenon occurs when massive objects warp spacetime, bending the light from objects behind them, allowing scientists to infer the distribution of dark matter. The large-scale structure of the universe is also analyzed through surveys of galaxy distributions. Understanding how galaxies cluster and interact provides essential information about the underlying forces shaping cosmic evolution. Current and future telescopes are set to enhance our observational capabilities significantly. Instruments like the James Webb Space Telescope are expected to provide unprecedented detail about the early universe and the formation of celestial structures. As cosmological observations continue to evolve, they play a critical role in testing theoretical models. The interplay between observation and theory drives advancements in our understanding of fundamental physics and the nature of the universe. Ultimately, cosmological observations are key to uncovering the mysteries of the cosmos. They help scientists piece together the history of the universe and explore the fundamental forces that govern its behavior. Gravitational wave detectors have revolutionized our understanding of the universe by enabling the observation of ripples in spacetime. These waves are generated by catastrophic events, such as the merger of black holes or neutron stars, providing a new way to study cosmic phenomena. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was the first facility to successfully detect gravitational waves in 2015. This landmark achievement confirmed a prediction of Einstein's general relativity and opened a new observational window into the universe. Gravitational wave detectors use laser interferometry to measure incredibly small changes in distance caused by passing waves. By comparing the lengths of two perpendicular arms, these instruments can detect the minute distortions in spacetime that result from gravitational events. The potential of gravitational wave astronomy extends beyond just detecting mergers. Observations can provide insights into the properties of black holes, including their masses, spins, and formation mechanisms, which are crucial for understanding their role in the universe. Detecting waves from neutron star collisions also offers valuable information about nuclear physics. Such events can reveal details about the behavior of matter under extreme conditions, helping to inform theories about the equation of state for nuclear matter. As research progresses, scientists are developing next-generation detectors, such as the Laser Interferometer Space Antenna, or LISA. This space-based observatory aims to detect lower-frequency gravitational waves, broadening the range of observable events and enhancing our understanding of the universe. Gravitational wave detections can also be combined with electromagnetic observations, creating multi-messenger astronomy. By correlating gravitational wave signals with optical or radio observations, researchers can gain a more comprehensive view of cosmic events. The study of gravitational waves has implications for testing general relativity in extreme conditions. Observations of waveforms from different sources can help validate or challenge existing theories about gravity and spacetime. These detectors also contribute to the exploration of dark matter and dark energy. By studying the dynamics of gravitational waves, scientists can investigate how these elusive components influence the universe's expansion and structure. In addition to their scientific applications, gravitational wave detectors represent a significant technological achievement. The engineering advancements required to build these sensitive instruments push the boundaries of measurement precision and experimental design. The future of gravitational wave astronomy looks promising, with ongoing developments in detection technology. As capabilities improve, researchers anticipate discovering new phenomena that could reshape our understanding of the cosmos. Ultimately, gravitational wave detectors serve as powerful tools for exploring the fundamental laws of physics. They invite a deeper investigation into the nature of gravity and its role in shaping the universe. Finding experimental evidence for theories of quantum gravity presents a significant challenge in modern physics. The energies required to probe the effects of quantum gravity often exceed the capabilities of current experimental technology, making direct observation difficult. One of the main hurdles lies in the extremely small scale at which quantum gravitational effects are expected to occur. The Planck scale, where these phenomena manifest, is around 10 to 35 meters, far beyond what can be achieved with existing particle colliders. Additionally, the weak nature of gravitational interactions complicates the detection of quantum effects. Unlike other fundamental forces, gravity is incredibly subtle, making it hard to isolate gravitational phenomena from other influences in experimental settings. Researchers also face challenges in identifying clear signatures of quantum gravity. Many proposed effects may not produce distinct or measurable outcomes, making it difficult to validate theories through experiments. Theoretical predictions often depend on complex models that can be difficult to test. Discrepancies between different models can lead to confusion about which aspects of quantum gravity to investigate experimentally. Another issue arises from the need for interdisciplinary collaboration. The exploration of quantum gravity involves insights from various fields, including theoretical physics, mathematics, and experimental design, requiring effective communication and cooperation. Laboratory experiments aiming to simulate conditions akin to those in quantum gravity must be meticulously designed. Ensuring that all variables are controlled can be a daunting task, often leading to challenges in reproducibility and reliability of results. Some researchers are exploring analog systems that mimic black hole conditions in controlled environments. However, translating findings from these analog experiments to real astrophysical phenomena remains a complex endeavor. Observational efforts, such as those targeting gravitational waves, offer potential avenues for indirect evidence. Yet these observations must be interpreted carefully to extract meaningful conclusions about the underlying quantum gravitational theories. The development of new technologies and methodologies is essential for advancing the search for experimental evidence. As capabilities improve, the hope is to achieve breakthroughs that could validate theories of quantum gravity. Funding and resource allocation for research in this area also pose challenges. Prioritizing projects that focus on quantum gravity among various competing fields can be a difficult balance for funding agencies. Despite these obstacles, the pursuit of experimental evidence for quantum gravity continues to inspire innovation and creativity. Researchers remain determined to uncover the fundamental principles governing the universe, navigating the complexities of this challenging field. Quantum cosmology explores the application of quantum mechanics to the entire universe, particularly during its earliest moments. This field aims to understand the fundamental processes that shaped the universe shortly after the Big Bang. One of the key areas of investigation is the concept of the wave function of the universe. This wave function encapsulates all possible states of the universe, providing a probabilistic framework for understanding its evolution. Models of the early universe often incorporate quantum fluctuations, which can have significant implications for cosmic structure formation. These fluctuations may have seeded the density variations that led to the formation of galaxies and clusters. The Hartle-Hawking no-boundary proposal is a prominent model in quantum cosmology. It suggests that the universe does not have boundaries in time or space, allowing for a smooth transition from a quantum state to a classical one. Another important approach is loop quantum cosmology, which applies the principles of loop quantum gravity to cosmological models. This framework aims to resolve singularities, providing insights into the Big Bang and the behavior of spacetime at extremely high densities. Inflationary models also play a critical role in understanding the early universe. These models propose a rapid expansion phase, helping to explain the uniformity of the cosmic microwave background and the large-scale structure of the universe. Quantum cosmology raises intriguing questions about time and causality. The interplay between quantum effects and classical time leads to discussions about how time behaves in the context of the early universe and its implications for our understanding of reality. Research in this field often employs sophisticated mathematical techniques, drawing on both quantum mechanics and general relativity. This interdisciplinary approach helps bridge the gap between quantum phenomena and cosmic evolution. Observational data, such as measurements of the cosmic microwave background, provides a testing ground for quantum cosmology models. By comparing theoretical predictions with observational evidence, researchers can refine their understanding of the early universe. The exploration of quantum cosmology also encourages philosophical inquiries about existence and the nature of reality. By questioning the origins of the universe, scientists are prompted to re-evaluate fundamental concepts about time, space, and causation. As advancements in technology continue, the potential for new discoveries in quantum cosmology grows. Ongoing research may uncover insights that significantly reshape our understanding of the universe's beginnings. Ultimately, quantum cosmology serves as a rich area of exploration, intertwining fundamental physics with profound existential questions. This field continues to inspire inquiry into the mechanisms that govern the cosmos and the nature of existence itself. The role of quantum gravity in understanding the Big Bang singularity is crucial for resolving the mysteries surrounding the universe's origin. This singularity represents a point where conventional physics breaks down, making it essential to apply quantum principles to comprehend what happened at that moment. Quantum gravity offers a framework for examining the extreme conditions present during the Big Bang. By integrating quantum mechanics with general relativity, researchers can explore how spacetime behaves in this high-energy environment. One of the primary goals is to determine how the universe transitioned from a quantum state to a classical one. This transition is key to understanding how the universe evolved from an infinitesimally small point to the expansive cosmos we observe today. Models such as loop quantum gravity suggest that spacetime may be quantized, helping to avoid the infinities typically associated with singularities. This quantization could provide insights into the structure of spacetime right at the moment of the Big Bang. The concept of the wave function of the universe is also significant in this context. It encapsulates all possible states of the universe, allowing researchers to analyze how quantum fluctuations influenced its early evolution. Exploring quantum gravity can also shed light on the nature of time at the Big Bang. Understanding how time behaves in this context may reveal whether time itself emerged during the Big Bang or if it has deeper origins. Inflationary models combined with quantum gravity provide a mechanism for understanding the rapid expansion of the universe following the Big Bang. These models suggest that quantum fluctuations during inflation could have seeded the structures we see today. Research continues to investigate the implications of quantum gravity for the initial singularity. By examining various theoretical approaches, scientists hope to construct a more coherent narrative about the universe's beginnings. Observational data from cosmic microwave background radiation provides a testing ground for these models. By comparing theoretical predictions with the patterns observed in the CMB, researchers can refine their understanding of the early universe. Interdisciplinary collaboration is vital in advancing research on quantum gravity and the Big Bang. By integrating insights from physics, mathematics, and cosmology, scientists can tackle the complex questions surrounding the universe's origin. The implications of quantum gravity extend beyond theoretical physics. They prompt philosophical inquiries about existence, reality, and the fundamental nature of the universe itself. As the study of quantum gravity continues to evolve, it remains a rich area of exploration. The quest to understand the Big Bang singularity drives researchers to seek new insights into the very fabric of reality and the origins of the cosmos. The role of quantum gravity in understanding the Big Bang singularity is essential for unraveling the universe's origin. This singularity signifies a breakdown of conventional physics, highlighting the need for quantum principles to interpret events at that critical moment. Quantum gravity provides a framework for investigating the extreme conditions present during the Big Bang. By merging quantum mechanics with general relativity, researchers can analyze how spacetime behaves in this intensely energetic environment. A primary focus is determining how the universe transitioned from a quantum state to a classical one. This transition is crucial for comprehending how the universe evolved from an infinitesimally small point to the vast cosmos we observe today. Models like loop quantum gravity propose that spacetime may be quantized, offering a way to avoid the infinities typically associated with singularities. This quantization may shed light on the structure of spacetime at the instant of the Big Bang. The wave function of the universe plays a significant role in this exploration. It encompasses all possible states of the universe, enabling researchers to assess how quantum fluctuations impacted its early development. Investigating quantum gravity also illuminates the nature of time during the Big Bang. Understanding the behavior of time in this context could reveal whether it emerged at the moment of the Big Bang or has deeper origins. Inflationary models that incorporate quantum gravity provide insight into the universe's rapid expansion after the Big Bang. These models suggest that quantum fluctuations during inflation may have seeded the structures we see in the universe today. Current research continues to explore the consequences of quantum gravity for the initial singularity. By examining various theoretical perspectives, scientists aim to create a more coherent narrative regarding the universe's beginnings. Data from cosmic microwave background radiation serves as a critical testing ground for these models. By comparing theoretical predictions with observed patterns in the CMB, researchers can enhance their understanding of the early universe. Collaboration across disciplines is essential for advancing research on quantum gravity and the Big Bang. By integrating insights from different fields, scientists can address the intricate questions surrounding the origins of the universe. The implications of quantum gravity reach beyond theoretical physics. They inspire philosophical inquiries about existence, reality, and the fundamental nature of the cosmos. As the study of quantum gravity evolves, it remains a vibrant area of investigation. The pursuit of understanding the Big Bang singularity motivates researchers to seek fresh insights into the essence of reality and the universe's origins. The study of quantum gravity has profound technological implications that could reshape various fields. As researchers delve into the quantum aspects of gravity, their findings may lead to advancements in materials science, particularly in developing new materials with unique properties. One potential application lies in the realm of quantum computing. Insights gained from understanding quantum gravity could inform the design of more robust qubits, enhancing their stability and performance in quantum information systems. The principles derived from quantum gravity research may also contribute to the development of advanced sensors. These sensors could utilize quantum effects to detect gravitational waves or subtle spacetime fluctuations with unprecedented sensitivity. In the field of energy generation, theories related to quantum gravity could inspire new methods for harnessing energy. Exploring the connections between gravitational forces and quantum mechanics might lead to innovative approaches for energy storage and conversion. Additionally, the intersection of quantum gravity and cosmology may yield new insights into astrophysical phenomena. Technologies designed to study black holes and gravitational waves could provide valuable data for understanding the universe's structure and evolution. Improvements in measurement techniques could arise from advancements in quantum gravity research. Enhanced precision in measuring gravitational effects could benefit various scientific disciplines, from fundamental physics to engineering applications. The exploration of quantum gravity may lead to breakthroughs in our understanding of dark matter and dark energy. Technologies that arise from this research could aid in detecting and characterizing these elusive components of the universe. Collaborative efforts between physicists and engineers can facilitate the translation of theoretical insights into practical applications. As quantum gravity research progresses, interdisciplinary collaboration will be essential for realizing its technological potential. In medicine, the principles of quantum mechanics might inform the development of new imaging techniques. Improved imaging technologies could enhance our ability to visualize biological structures at unprecedented resolutions. Quantum gravity concepts could also inspire advancements in communication technologies. By leveraging quantum entanglement and other phenomena, new methods for secure communication may emerge, revolutionizing data transfer and encryption. The influence of quantum gravity extends to philosophical discussions about the nature of reality and technology's role in shaping our understanding. Engaging with these implications can encourage deeper reflections on the ethical considerations surrounding new technologies. As research in quantum gravity continues to evolve, its technological implications will likely expand. The potential for new innovations promises exciting opportunities across various fields, driven by our quest to understand the fundamental nature of the universe. Future predictions and uses of quantum gravity theory promise to reshape our understanding of the universe. As researchers continue to explore the interplay between quantum mechanics and gravity, we may gain insights into the fundamental nature of spacetime itself. One significant area of prediction involves the behavior of black holes. Understanding quantum gravitational effects could lead to new models that describe the internal structure of black holes, potentially resolving the information loss paradox. In cosmology, advancements in quantum gravity theory might provide better explanations for dark matter and dark energy. New insights could help clarify the role these mysterious components play in the universe's evolution and expansion. Another promising avenue is the potential for breakthroughs in quantum computing. The principles of quantum gravity could inspire more stable qubit designs, leading to enhanced performance and scalability in quantum systems. Research in quantum gravity may also pave the way for innovative technologies in gravitational wave detection. Improved theoretical models could enhance our ability to detect and analyze gravitational waves from distant cosmic events. The implications for high-energy physics are equally exciting. Future colliders may be designed with the insights gained from quantum gravity theory, allowing for tests of phenomena that occur at energies close to the Planck scale. Educational applications are also on the horizon, as quantum gravity theory could inspire new curricula in physics. Engaging students with concepts that bridge quantum mechanics and relativity may encourage a deeper understanding of fundamental physics. Collaboration between disciplines will likely play a crucial role in harnessing the potential of quantum gravity theory. By integrating insights from mathematics, theoretical physics, and engineering, researchers can develop innovative approaches to practical applications. The exploration of quantum gravity may influence our understanding of time itself. As we unravel the nature of spacetime, new theories could emerge regarding the flow of time and its implications for both physics and philosophy. Quantum gravity research is expected to drive advancements in observational astrophysics. Improved models may lead to better interpretations of data from telescopes and detectors, enhancing our understanding of cosmic events. Future predictions also include the development of new experimental techniques inspired by quantum gravity principles. These innovations could enable more precise measurements of gravitational phenomena, expanding the frontiers of experimental physics. Ultimately, the ongoing investigation of quantum gravity theory is poised to yield transformative discoveries. The potential applications and insights derived from this research promise to deepen our comprehension of the universe and our place within it. In this video, we delved into the fascinating realm of quantum gravity, exploring its significance in understanding the universe. We began by discussing the fundamental concepts of quantum gravity and how it seeks to unify the principles of quantum mechanics with general relativity. We examined the roles of various theories, such as loop quantum gravity and string theory, in addressing the complexities of gravitational interactions at quantum scales. We also highlighted the challenges faced in detecting experimental evidence, emphasizing the need for advanced technologies and collaborative efforts in research. The implications of quantum gravity extend into cosmology, where it helps us explore the mysteries of the Big Bang singularity and the evolution of the universe. We looked at the role of observational data, including the cosmic microwave background and gravitational wave detections, in refining our understanding of these complex theories. Additionally, we discussed the potential technological advancements arising from quantum gravity research, including innovations in quantum computing and new methods for detecting gravitational waves. The future predictions regarding the practical applications of quantum gravity theory promise to shape various fields of science and technology. As we conclude our exploration of quantum gravity, we encourage you to reflect on the profound questions it raises about the nature of reality and the universe. If you enjoyed this video and found it insightful, please like and subscribe to our channel. Your support helps us continue creating content that dives into the wonders of physics and beyond. Don't forget to check out the rest of our videos, where we explore a variety of topics related to science, technology, and the mysteries of the cosmos. Join our community of curious minds as we embark on this journey of discovery together. Your engagement not only motivates us, but also enriches the conversations we share. Thank you for watching, and we look forward to bringing you more fascinating insights into the world of science. Stay curious and keep exploring the universe with us.